What if I told you time actually moves slower the faster you go, like real time? What if gravity isn't even a force, but just the way space folds in on itself? These aren't sci-fi ideas. They're straight from Einstein's notebook. And here's the wild part. He didn't just rewrite the rules of physics, he flipped reality on its head. The stuff you're about to hear, it's so strange, so brilliant, you'd swear it came from another dimension. But it didn't. It came from the most famous thinker in human history. So yeah, this isn't just some background noise to snooze to. This is 3 hours of the deepest, weirdest, most beautiful truths about the universe, gently wrapping around your thoughts as you drift off. Because tonight you're not just falling asleep. You're falling into Einstein's mind. But before that, I'd love to invite you into our cozy corner of the internet. Drop a quick comment and let us know where are you watching this from, and what time is it for you. It's pretty cool how we're all connected, searching for that perfect night's sleep. If these Einstein's wildest ideas light up something in you, go ahead and subscribe our channel RestWise. Now, get comfy and let these Einstein's wildest ideas guide you into a peaceful sleep. Time slows down as you move faster. Okay, let's kick things off with one of Einstein's most famous and freakiest ideas. The faster you move, the slower time passes for you. No, really, not metaphorically. Not in some poetic, live life in the moment kind of way. I mean literally, physically. According to Einstein's theory of special relativity, time itself doesn't tick at the same rate for everyone. It's not a universal clock just chugging along in the background. Instead, time bends, depending on how fast you're moving. Let me give you a wild example to paint the picture. Imagine you have a twin. You both look the same, think the same, and are exactly the same age, until one of you decides to hop on a spaceship and fly near the speed of light, let's say 99.999% the speed of light. Just, casually zooming through the galaxy at mind-melting velocity. The other twin, they stay on Earth. Maybe working a 9 to 5, feeding their cat, scrolling TikTok. Nothing unusual. Now, here's where it gets weird. After a few years on the ship, the traveling twin decides to come back. And when they do, they've barely aged at all. Maybe a few months have passed for them, but their twin on Earth, decades older, same genes, same birth date, but completely different biological clocks. That's not a Cephas story. That's time dilation, a real effect confirmed by physics. And this isn't just some abstract theory either. We've actually tested this with real-world experiments. Back in the 1970s, scientists took super precise atomic clocks, synced them up perfectly, and then flew one of them around the world on a commercial jet. The result, when they reunited the two clocks, they were off, just by a tiny bit, but enough to prove Einstein right. Time on the moving clock had actually ticked slower. The faster one moved, the slower time passed for it. Now you might be wondering why. What's causing that? Here's the simple but brain-breaking explanation. According to special relativity, the speed of light is constant. It never changes, no matter how fast you're moving. Light will always hit your eyeballs at the exact same speed, about 300,000 kilometers per second, even if you're sprinting toward it or running away. So in order to keep that speed constant for everyone, the universe has to do something kinda sneaky. It has to adjust the way time flows, and even the way distances stretch and shrink. Time slows down, distances contract. It warps space and time themselves to make the math work. Think about that for a second. The universe would rather bend time itself than let light speed up or slow down for different people. That's how sacred the speed of light is. Kinda makes you feel small, doesn't it? But also weirdly special. Because this isn't just a curiosity, it has massive implications. For instance, let's say one day in the far future, humans actually build a spaceship that can travel at near light speed. If you're on that ship for, Say, 5 years you could come back and Earth might be 500 years older. You'd return to a planet you barely recognize. Cities changed. Entire generations gone. Time didn't stop for you, but it slowed just enough to make your journey a one-way ticket into the future. That's not just trippy. That's time travel, no wormholes required. Just go fast enough, and the future will come to you. But wait, here's something even more mind-warping from your point of view on the spaceship. Everything feels normal. Your watch still ticks like always. Your coffee still takes 5 minutes to cool down. You feel no difference at all. It's only when you compare clocks with someone back on Earth that things get strange. That's because time is relative. It's not absolute. It depends on your frame of reference, your motion through space. Einstein's whole idea was that the laws of physics should look the same no matter how fast you're going, as long as you're not accelerating. That's what we call an inertial frame. And in those frames, there's no true time. There's only your time, their time, and the space between. Here's a metaphor I like to use. Think of time like a river. If you're standing still, it flows gently past you. But if you hop in a speedboat and start flying down that river at top speed, the flow seems slower relative to the bank. That's your time dilating. You're still moving through time, but the way you experience it depends on your velocity. Faster movement equals to slower time. And the closer you get to the speed of light, the more dramatic it gets. And here's the kicker, you can never actually reach the speed of light. Why? Because as you get faster and faster, time keeps slowing down, and your mass sort of increases. It's like trying to run through syrup that keeps getting thicker the faster you move. Eventually, the universe just says, nope. That's fast enough. So the speed of light isn't just a speed, it's a cosmic speed limit, a built-in boundary to the universe's code, a line that only light and maybe gravity gets to cross. The rest of us are stuck below it, forever playing catch-up in a world where time bends to motion. And honestly, that's beautiful, because it means the universe isn't rigid, it's flexible, it adapts, it responds to how you move. You're not just floating through time and space, you're literally reshaping them as you go. Time slows down as you move faster, and the faster you go, the stranger reality becomes. Mass and energy are the same thing. All right, next up. This is the idea that literally changed the world. You've probably heard the equation before. Energy equals mass multiplied by the speed of light squared. Yeah, that one. The famous one. The one scribbled on chalkboards, printed on T-shirts, and whispered dramatically in every science documentary ever made. But here's the thing. Most people know the equation, they just don't know what it means. So let's unpack it. Slowly. Simply. Like we're just talking on a walk. What Einstein figured out is that mass and energy aren't two different things. They're just two different forms of the same thing. Like steam and water, same substance, different appearance. Mass is energy. Energy is mass. And they're connected by one of the biggest numbers in nature, the speed of light, squared. Which is a lot. Like really a lot. The speed of light is already fast enough. Roughly 300,000 kilometers per second. Now square that, you're multiplying it by itself. You're in brain exploding levels of energy, territory. So here's what this really means in everyday terms. Even a tiny amount of mass has an absolutely massive amount of energy locked inside it. Like, take something super small. A paperclip. Looks harmless, right? But if you could somehow convert all the mass of that little paperclip directly into energy, no waste, no leftovers, you'd release enough energy to blow up a city. That's how powerful the mass-to-energy relationship is. That's how deeply the two are connected. Now don't worry, your office supplies aren't about to vaporize on their own. That kind of conversion doesn't just happen easily. It takes extreme conditions, like the inside of stars. or the heart of a nuclear reaction. And yep, this is the exact principle behind how nuclear energy works. Whether it's powering your city, or in more unfortunate chapters of history, destroying one. In a nuclear reaction, atoms are split or fused together, and when that happens, a little bit of mass goes missing. Like poof, just disappears. But it doesn't really disappear. It transforms. It becomes energy, massive energy. The universe caches in that little bit of mass and gives you a cosmic explosion in return. All thanks to energy equals mass multiplied by the speed of light squared. But let's zoom out beyond bombs and reactors. This idea, the idea that mass is energy, completely rewrote how we see matter itself. It means that matter isn't just stuff. It's not just sitting there. It's potential. Every atom, every particle, every grain of sand is holding on to some amount of locked-up energy just by existing. The chair you're sitting on, full of it. Your body, packed with it. The moon, the trees, the phone in your hand. All of it is stored energy waiting to be released under the right conditions. And this wasn't just a scientific curiosity. It solved a puzzle that had been bugging physicists for years. See, before Einstein, people thought of energy and mass as separate things. You had mass, like bricks and people and planets. And you had energy, like light and heat and motion. They were different categories. But this one idea, that they're the same thing in disguise, unified everything. It brought physics closer together. It connected matter and energy into a single, elegant concept. That's the thing about Einstein. He had this gift for seeing unity where other people saw chaos, and this equation, this simple, looking statement, was the beginning of that vision. Now here's something a little deeper to think about. In a way, this idea also tells us something poetic about us. We are not just made of matter. We're made of energy, condensed, vibrating, interconnected energy. And that means you listening to this right now, are literally part of the same energy system that lights up the stars. The same physics that powers the sun is inside you. Not metaphorically, literally. That's not just science. That's something kind of beautiful. And here's another twist. This idea also works in reverse. Energy can become mass, too. When you smash particles together at high speeds, like we do in giant machines called particle accelerators, you can actually create mass out of energy. You can make particles appear from pure energy, like magic pulled from the laws of physics. So in both directions, mass to energy and energy to mass, this equation is the bridge. It's not just about big explosions or dramatic reveals. It's about understanding that reality is fluid, that what looks solid is actually just energy, frozen in place by gravity and time and the laws of nature. And once you see that, you can't unsee it. It changes the way you look at the world, the way you look at matter, the way you look at yourself. Energy equals mass multiplied by the speed of light squared. It's not just an equation. It's the universe's way of saying everything is more than it seems. Gravity is the curving of spacetime. All right, so here's where things start getting seriously next level. We've talked about how time slows down when you move faster. We've talked about how mass is just energy dressed up in matter clothes. But now we get to gravity, and what Einstein said about it flipped the entire universe on its head. Because here's the deal. Gravity is not a force, not in the way we used to think, not like a string pulling things downward. In fact, according to Einstein, gravity isn't something that pulls at all. Instead, it's something that bends. And what it bends is spacetime itself. Let me explain. Imagine the universe as a giant rubber sheet, flat, stretched out in all directions. That's spacetime, the fabric of the cosmos. Now, if you place something small on it, like a marble, nothing really happens. The sheet stays pretty flat. But what if you drop something heavy onto it, like a bowling ball? The sheet curves. It dips downward. The bigger the ball, the deeper the curve. Now imagine rolling a marble across that curved sheet. What happens? It starts to spiral inward, not because there's a mysterious force pulling it, but because it's just following the curve. It's moving in a straight line through a curved space. That, right there, is gravity. It's not a force. It's just the way things move when spacetime is warped by mass and energy. And this is the heart of Einstein's theory of general relativity. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. It's such a beautiful idea, right? It turns the universe into something almost alive, responsive, stretchy. Big things, like stars and planets and black holes, bend the very fabric of reality around them. And that bending is what we feel as gravity. When you drop an apple and it falls to the ground, it's not being pulled in the traditional sense. It's just following the curve of spacetime that Earth's mass creates beneath it. You're not being pulled down. You're falling into a dip in the cosmic mattress. And the deeper the mass, the more dramatic the curve. A planet curves spacetime. A star bends it even more. But a black hole, that's where spacetime just gives up. It curves so sharply, so violently, that not even light can escape. We'll talk more about black holes later, but just keep this image in your head. The universe is like a soft surface, and gravity is just what happens when something heavy sits on it. Now, here's the cool part. We didn't just take Einstein's word for it. We've actually seen this effect. One of the first big pieces of proof came in 1919 during a solar eclipse. A group of astronomers, led by Sir Arthur Eddington, looked at stars that appeared near the edge of the sun. And guess what? The stars looked like they were in slightly different positions than usual. Why? Because the light from those stars had to pass near the sun on its way to Earth, and the sun's mass bent spacetime, which bent the path of that light. The stars hadn't moved. Spacetime had. That one experiment instantly made Einstein a global icon. His theory had predicted the effect years before, and now it was proven true. A new era of physics had begun, and since then, we've seen this bending of spacetime happen all the time. We use it, actually. GPS satellites, floating above Earth, have to correct for the effects of both motion and gravity warping time. The clocks in orbit tick differently from the ones down here, thanks to relativity. If we didn't account for the curve of spacetime, your GPS would be off by miles. Like, take a wrong turn and end up in the next state level of wrong. That's how real this is. This isn't theory anymore. It's tech, it's maps, it's reality. Now, let's go just one layer deeper. Einstein didn't just stop at explaining gravity. He showed that mass and energy warp space and time together. That's why we call it spacetime, because you can't separate one from the other. When mass warps space, it also warps time. That's why time runs slower near massive objects, like we'll see in another section. The deeper you fall into a gravity well, the more stretched time becomes. So the next time you feel the tug of gravity, I want you to imagine this. You're not being pulled down. You're coasting through a landscape that's been gently bent by the Earth beneath you. You're surfing a slope in spacetime. You don't feel it. You don't see it. But every step you take is following the curve of a universe that's constantly shifting under your feet. And that shift, that's gravity, not magic, not a mysterious force, just geometry. Elegant, invisible, cosmic geometry. And all of it, every falling apple, every orbiting moon, every spinning galaxy, is obeying the curves in this grand, silent fabric. The universe doesn't pull things. It shapes the stage they move on. And that one idea, that gravity is the bending of spacetime, has given us black holes, gravitational waves, and a completely new way to understand the dance of everything. All because Einstein stopped thinking about gravity as a force and started seeing it as a shape. Simultaneity is an illusion. Okay, here's one that's going to quietly blow your mind. We're so used to thinking of time as this universal thing, right? Like a single clock ticking away, same for everyone, everywhere. But according to Einstein, nope, time doesn't work like that. In fact, what you think is happening now might not be happening now for someone else. Seriously, this is the idea of simultaneity, and Einstein showed us. It's not actually real. Simultaneity is an illusion. Let's break that down gently. Imagine you're standing in the middle of a train platform. Everything's still, peaceful. There's a train passing by, and as it zooms by, bam, two lightning bolts strike at either end of the platform. One hits the front of the train track, one hits the back. From your perspective, standing still on the platform, you see both bolts at the same time. Seems obvious, right? Two flashes, same moment. Done. But now imagine someone's riding on that moving train. They're sitting exactly in the middle of the train car as it passes through the station. To them, something completely different happens. Because the train is moving forward, the person on board is moving toward the spot where the front lightning bolt hit and away from the back one. So the light from the front strike reaches them just a tiny bit before the light from the back does. From their perspective, the bolts didn't happen at the same time. The front one happened first. Wait, yeah, two people, both right in the middle, both watching the exact same event, and they completely disagree on what just happened. But they're both right. That's the twist. Neither person is wrong. Because according to Einstein's special relativity, there's no absolute now. There's no universal timeline that everything agrees on. What's simultaneous for you might not be simultaneous for someone else moving at a different speed. That's not just a weird science trick. That's how time actually works in the universe. It's not fixed. It's not shared. It's relative. To motion, to position, to who's watching. The faster you're moving compared to someone else, the more your version of now disagrees with theirs. Think about how wild that is. That means if someone's moving fast enough, like on a spaceship near the speed of light, their version of what's happening on Earth right now might be our past, or even our future. That's not science fiction. That's just physics. This is where time really starts to stretch and flex like taffy. There's no single timeline we're all sitting on together. Every person, every observer, has their own personal thread through spacetime. Einstein didn't just say, time is relative. He said, events themselves aren't universally ordered. There's no one-size-fits-all sequence of events. The universe isn't running on one shared clock. It's like each of us is living in our own slightly different reality, our own slightly different now. And yeah, I know that sounds like philosophy, but it's not. This is the measurable, testable heart of special relativity. Here's a real-world example: the Global Positioning System, GPS. Those satellites orbiting the Earth are moving fast, and they're also farther from the center of gravity, which we'll get into in a later section. But the key point here is that their clocks tick differently than ours. If we didn't adjust for the differences in their experience of time, and yes, including differences in simultaneity, GPS wouldn't work. Your map app would put you in the wrong city. So this illusion of simultaneity, it's not just a mind game. It's built into how we navigate the world. Let's slow this down even more. We think of moments, birthdays, sunsets, a kiss, the first time you saw the ocean, as little pearls on a string. A timeline, right? But that string, it doesn't exist the same way for everyone. Someone far away moving fast enough wouldn't line up those moments in the same order. For them, maybe the kiss happened before the sunset, or your birthday after they saw the ocean. Not because they're wrong, but because their movement warps their slice of time. Einstein showed us that time and space are not separate things. They're woven together into spacetime, and how you move through space changes how you move through time. So once you accept that, the idea of one universal now kind of falls apart. It's like asking what's the top of the mountain when you haven't said which mountain now is local. It's personal, and honestly, that's kind of beautiful. The universe isn't giving us some master clock. It's letting us each move through our own version of time. That also means time travel, in some form, isn't just fantasy. If two people experience time differently based on their speed, then the future and the past are already baked into spacetime. They're just waiting for someone to reach them from the right angle. So yeah, simultaneity. Not real, just a useful illusion we've all agreed on, because we're all moving slowly relative to one another. But once you really start zooming through the cosmos, it melts away. And what's left? A universe where time flows differently for everyone. A universe where now is a matter of perspective. A universe where your reality is yours and no one else's is exactly the same. Kinda makes you feel like a time traveler already, doesn't it? Light has no rest frame. Alright, buckle up. Because this one messes with your intuition in the best way possible. Have you ever wondered what it would be like to just ride a beam of light? Like, you hop on and coast through space at light speed. You're soaring across the universe, galaxies streaking by, time standing still. Yeah, that whole idea. Einstein says no, that's not how light works. In fact, it can't work like that. Because light has no rest frame. Let's take a minute to unpack that, nice and slow. Imagine a car driving past you at, say, 60 miles an hour. If you're standing still, that car is zooming by pretty fast. But if you're in another car going 50 miles an hour in the same direction, the first car only seems to be going 10 miles an hour faster than you. Makes sense, right? You compare its speed to yours. That's how speed normally works. You subtract. But light doesn't play by those rules. Light always moves at the exact same speed, no matter how fast you're going. Whether you're standing still, driving, flying, or even on a spaceship going 99% the speed of light, it doesn't matter. If you measure the speed of light, you'll always get the same answer, around 186,000 miles per second. That's not just weird. That's unprecedented. Because it means you can't catch up to light. You can't ride alongside it. You can't even get close enough to slow it down. Light is always moving at the speed of light, and nothing ever sits at that speed. That's what we mean when we say light has no rest frame. There's no such thing as seeing what light sees. You can't press pause on a photon and ask, hey, what does the universe look like to you? Because the moment you try to sit still with light, you stop being real, physically speaking. The laws of physics don't allow anything with mass, me, spaceships, to move at the speed of light. Because as you accelerate, your energy increases. And to reach light speed, you'd need infinite energy. And infinite energy, not gonna happen. But photons, particles of light, are massless. That's the loophole. They don't need to accelerate to light speed. They're born moving at it. It's like they don't live in time at all. They don't speed up. They don't slow down. They don't sit still. They just go. And that's wild to think about, because it means from the perspective of a photon. If we could even imagine such a thing, the entire journey from one point to another happens instantly. Like, a photon could be emitted from a star 10 billion light years away, travel across the universe for billions of years by our clocks, and then hit your eye. Whoa, but from the photon's point of view, that journey had zero duration. It just happened, boom, start to finish, no ticking clock, no in between. It's like light doesn't experience time. That's one of the strangest implications of Einstein's theory. The faster you go, the slower time moves for you. And since light moves at the absolute speed limit of the universe, its internal clock, if it had one, is frozen. So no riding the beam, no seeing what it sees. because in a very real way light doesn't see anything. It doesn't experience anything. It just exists at the boundary of space and time, connecting moments like a bridge. And here's the twist. This constant speed of light, that stubborn refusal to change no matter who's watching, isn't just a fun trivia fact. It's the foundation of Einstein's entire theory of special relativity. Think about that. One rule, one weird fact: the speed of light is the same for everyone. And from that we get time slowing down when you move faster. We get length shrinking. We get mass increasing. We get the breakdown of simultaneity. We get all of it. It's like the universe said, okay, I'm going to pick one thing, just one, and make it absolutely unchangeably constant. And that one thing, light. Not your speed, not your clock, not even your idea of what now means, just light. And everything else has to adjust to keep that constant intact. It's one of the most beautiful ideas in physics, that reality bends to preserve this one universal rule. And because of it, light becomes this strange kind of cosmic ghost, always moving, never resting, never slowing, never stopping. The fastest thing in the universe, but also the thing that doesn't live in time. So the next time you see sunlight streaming through your window, or headlights cutting through the fog, or a shooting star streaking across the sky, take a moment to think about what you're really seeing. You're watching something that never stopped, never paused, never had a moment of rest. It left its source and traveled across space, not in seconds, not in hours, but in a timeless instant as far as the photon is concerned. And yet we see it, we feel it, we live by it. Light is how we know the universe, how we measure it, how we explore it, and still we'll never ride it, because to do that, you'd have to leave behind time itself. Your mass increases as you accelerate, ready to stretch your brain a little more, because we're about to talk about something that sounds almost like science fiction. But it's not. It's a real consequence of Einstein's theory of special relativity. And here it is: the faster you move, the heavier you get. Yup, you heard that right. As your speed increases, your mass, your resistance to acceleration, increases too. And no, I'm not talking about eating a burrito and going for a run. I mean your actual physical mass increases just because you're moving faster. Let's slow this all the way down and really get into what that means. In everyday life, we think of mass as this fixed thing, right? You weigh 150 pounds on Monday, you weigh the same on Tuesday, unless you had an epic cheat day. But when you start moving really, really fast, like a significant fraction of the speed of light, mass stops being this constant, fixed number. It starts to change. And that change happens because of how energy and mass are tied together. Remember Einstein's most famous idea: energy equals mass multiplied by the speed of light squared. That little formula packs a massive punch. What it's saying is that mass and energy are just two versions of the same thing. They're interchangeable, connected. So when something starts to move faster, its kinetic energy increases. And because of that, its effective mass increases too. It gets harder and harder to accelerate it further. Not because it's dragging its feet, but because the universe itself resists that extra push. Let me give you a picture. Imagine you're driving a car. At slow speeds, pressing the gas pedal gives you a smooth, predictable acceleration. Easy. But now imagine that for every 10 miles an hour faster you go, your car gets heavier, not by a little, by a lot. So now every extra burst of speed needs more force than the last. And the faster you go, the more impossible it becomes to keep accelerating. That's what happens to anything with mass as it approaches light speed. Its mass increases, not just in the way you might weigh more on a different planet or in a stronger gravity field, but in how it behaves in the universe, how it reacts to force, how it resists motion. At normal speeds, you don't notice it. The change is so tiny, it's basically nothing. But when you're approaching, say, 90% the speed of light. Your mass has increased significantly, and at 99.99% of light speed, the energy required to push you faster becomes infinite. That's the key. You can never actually reach the speed of light because you'd need infinite energy to do it. Why? Because your mass would become infinite too. That's the universe saying, hey, buddy, light speed is reserved. Not for you. Only massless particles, like photons, can move at light speed. Everything else, you can get close but never quite there. Now, just to be clear, modern physicists don't often talk about relativistic mass anymore. Today we usually talk about an object's invariant mass. That's the mass that doesn't change, no matter how fast you go. But back when Einstein's ideas were fresh and new, this notion of mass increasing with speed helped people wrap their heads around what was happening. And it still works as a way to feel what's going on. So when we say your mass increases as you accelerate, what we're really saying is it becomes harder and harder to speed you up because your energy, and thus your inertia, is growing. In other words, motion itself changes who you are in the eyes of the universe. You might be the same person, but you're harder to move. Heavier in a very real, physical sense. Want a real, world example? Particle accelerators. We've built these massive machines, like the Large Hadron Collider, that fling tiny particles around at incredible speeds, close to light speed. And those particles, they become incredibly difficult to accelerate the closer they get to the cosmic speed limit. Scientists pour more and more energy into them, but the speed barely increases. That's because that energy is going into making them heavier. The particles are gaining relativistic mass. That's what's happening right there in the lab. So this isn't just theoretical. We see it. We use it. It's how we smash atoms and unlock the secrets of the universe. Think about what that means. You can't keep speeding up forever. The universe fights back, and not because it's being stingy, but because of how space and time are knitted together. It's all part of the grand cosmic safety mechanism. Light speed is the hard limit. You can flirt with it, but you'll never touch it. The closer you get, the heavier you become, until you're carrying the weight of a star on your shoulders. So yeah, your mass increases as you accelerate, and that's not just a cool physics fact. That's a cosmic reminder the universe has boundaries, energy has consequences, and even motion bends the rules of reality. So next time you imagine a spaceship flying through the galaxy at warp speed, remember this: it's not just about going fast. It's about pushing against the very structure of space and time. And as you get faster, the universe pushes back. Black holes are real consequences of space-time curvature, a right time to fall into the abyss. And I mean that literally, because Einstein's equations, those beautiful, mind-bending equations that changed the way we think about gravity, lead to one of the most terrifying, fascinating, and strangely elegant objects in the universe: black holes. Now here's the wild part. Einstein didn't like them. He didn't believe they could actually exist out there in the real universe. He thought they were just a weird mathematical possibility, an edge case, a glitch in the math. But his own theory, it said otherwise. It said, yup, these things are not only possible, they're inevitable. So let's rewind a little and build up to what that means. When Einstein developed his general theory of relativity, he basically flipped the script on gravity. Instead of saying gravity is a force that pulls on objects, like Newton described, he said, gravity is what happens when mass and energy curve spacetime. Imagine the universe as a giant, stretchy fabric. When you place something massive on it, like a planet, a star, or a galaxy, it causes a dip in that fabric. Other objects, like smaller planets or even light, roll along those curves. That's what we feel as gravity. No mysterious force pulling things, just geometry. And here's where it gets intense. because the more mass you cram into a small space, the deeper that curve gets. And if you push it far enough, if you compress enough mass into a tight enough region, something snaps. The curve becomes so steep, so extreme that nothing, not even light, can climb out. That's a black hole. A region where space-time is so distorted, so tightly pinched, that escape becomes impossible. Not because there's a wall, not because there's something sucking things in, but because the rules of space-time itself say nope, you're not getting out of here. Now, black holes weren't just made up by science fiction writers. They were first predicted by solving Einstein's equations. Just a few months after Einstein published general relativity, a German physicist named Karl Schwarzschild found an exact solution to those equations that described the spacetime around a single spherical mass. And hidden in his solution was something radical. If the mass was concentrated tightly enough, it would form what we now call a black hole. But again, even though the math was solid, Einstein didn't buy it. He thought nature would find a way to prevent that kind of extreme collapse. Turns out, nature didn't care what Einstein thought, because not only do black holes make mathematical sense, we've actually seen the evidence. In fact, we've been seeing it for decades. We've watched stars orbiting invisible objects, whipping around at speeds that make no sense unless there's something incredibly massive packed into a tiny space. We've observed light bending around regions of space, forming rings, what we call gravitational lensing, that point to a massive, invisible presence. And in 2019, we finally got a picture. That orange donut-looking thing with a dark hole in the center. That's not CGI. That's the shadow of a black hole, captured by a global network of telescopes acting as one giant eye. And just in case you were wondering if it was a fluke, they did it again in 2022. This time with the supermassive black hole at the center of our own galaxy. These things are real. They're out there. And they are a direct consequence of how Einstein said gravity works. Here's the cool part, though. A black hole isn't just a monster in space. It's a window into the most extreme physics we know. At the center of a black hole, what we call the singularity, our current understanding breaks down. The curvature of spacetime becomes infinite. Density becomes infinite. Time and space swap roles. It's not just a place. It's a region where our equations start screaming for a new theory. Something deeper. Something quantum. Something we haven't fully discovered yet. And that's part of what makes black holes so special. They're not just cosmic garbage disposals. They're test grounds for our deepest theories. A place where relativity and quantum mechanics collide. A place that dares us to go further. But even beyond the science, there's something poetic about black holes. Think about it. A black hole is the final chapter in the life of a star. After millions or even billions of years of burning bright, a massive star collapses in on itself, not with a whimper, but with such violence that it tears a hole in the fabric of the universe. And yet it leaves behind something eternal, a silent, invisible reminder of its once fiery existence. You can't see it directly, you can't touch it, but you know it's there. By the way it shapes everything around it. It bends light, it warps time, it anchors galaxies, and maybe, just maybe, it holds the key to something deeper. So yeah, Einstein didn't believe in black holes, but his math did. And now, the universe has proven them both right. Gravity isn't just a pull, it's a curve, a twist, a ripple, and sometimes that curve becomes so deep that even light can't climb out. That's not science fiction. That's spacetime at its most dramatic. That's a black hole. Light bends around massive objects. Okay, so you've heard the phrase seeing is believing, right? Well, what if I told you that even light itself doesn't travel in a straight line when the universe decides to mess with it? Seriously, Einstein predicted that massive objects can bend light, like a planet or a star curving the path of a beam. as if space itself were a lens. And it sounds completely bonkers until you realize it's been tested, confirmed, photographed. And it actually rewrote what we thought we knew about the universe. Let's unpack that. In Newton's world, gravity only affects mass. Objects with weight, apples falling from trees, moons orbiting planets. But light, it has no mass. It shouldn't be affected by gravity at all, right? Well, Einstein had a very different idea. In general relativity, gravity isn't a force. It's the bending of space and time by anything that has energy or mass. So when light passes near a massive object, like a star or a galaxy, it's not being pulled by gravity like a rock or a satellite. It's following the curved path of spacetime around that object. In other words, light is still moving in a straight line. It's just that straight lines themselves get bent in curved space. It's like laying a laser pointer on a trampoline. If the trampoline is flat, the beam goes straight. But place a heavy bowling ball in the middle, and the trampoline curves. And suddenly that laser path gets warped too. That's what happens in space, and this wasn't just a pretty theory on paper. It was put to the test. Here's how it went down. In 1919, British astronomer Sir Arthur Eddington led an expedition to photograph a solar eclipse, a rare moment when the moon blocks the sun's light, allowing us to see the stars near its edge. According to Einstein's predictions, the stars behind the sun, just behind its edge, should appear slightly out of place. Why? Because the sun's mass was bending the light from those stars, curving it as it passed by. If Einstein was right, the starlight would veer around the sun's edge, shifting their apparent positions in the sky. And sure enough, when Eddington developed the photos, he saw it. The stars looked displaced, exactly the amount Einstein's equations predicted. And in that moment, the world changed. Einstein became a global celebrity overnight, not because of a flashy speech or a wild discovery, but because the universe quietly whispered, he's right. The fabric of space could bend, and light, our most constant, fastest traveler, would bend with it. This phenomenon has a name now. We call it gravitational lensing. And it's not just some old historic curiosity. It's something we still use right now to study the universe. In fact, we've spotted galaxies that appear stretched or duplicated in strange ways, because their light passed by other galaxies or dark matter on its way to us. Those cosmic masses act like magnifying glasses, distorting the images of whatever lies behind them. That's gravitational lensing in action. And we use it like a cheat code to see things we'd never be able to see otherwise. It helps us detect black holes, hidden galaxies, and even map out the invisible dark matter that doesn't emit light at all, but still warps space. The craziest part, we're using light bending, something we once thought was impossible, to find the things that are completely invisible. I mean, how poetic is that? The thing that was supposed to travel in perfect, straight lines now bends gently around stars, planets, galaxies, like it's flowing along a cosmic riverbank. It's one of those ideas that quietly transforms how you see the world, because it means space isn't just empty, it's active, it's shaped, it has texture and curves and valleys. And even the fastest thing in the universe, light, can't escape those curves. It flows along them, obeys them, dances with them. And you know what's even more beautiful? We wouldn't even be able to see some parts of the universe without this effect. Gravitational lensing has shown us galaxies from billions of years ago, because the light from those galaxies curved around massive clusters and found its way to us. So we're literally seeing the ancient universe thanks to a prediction Einstein made in a paper over 100 years ago. That's not just science. That's poetry written in the fabric of space. So the next time you look up at the night sky and see a star twinkling back at you, think about this. That light might have taken a detour. It might have curved around a massive object on its way here, skimming a galaxy, bending gently through warped spacetime, just to land softly in your eye. A journey through curved space, a cosmic shortcut, a beam of light shaped by gravity. Einstein once said that imagination is more important than knowledge. But sometimes the universe has the best imagination of all. And light, it doesn't always go straight, not when space itself decides to curve. Time runs slower in gravitational fields. So, what if I told you that time doesn't tick at the same rate everywhere in the universe? Sounds crazy, right? But according to Einstein, again, it's not just true, it's been measured, and not in some sci-fi movie, but in real life. Time, actual time, runs slower when you're closer to something massive. Think of it like this: the more gravity you're feeling, the more time chills out. It stretches. It dilates. This isn't just theory, it's something your phone relies on. But we'll get to that in a bit. Let's rewind for a sec. You already know that Einstein turned our idea of gravity on its head. He said gravity isn't a force pulling things down. It's the curving of spacetime caused by mass. But when space curves, time curves too. Because in Einstein's world, space and time aren't separate things. They're woven together into one fabric, spacetime. And when that fabric bends, it affects everything, including the speed at which time flows. Here's the visual: imagine spacetime as a giant rubber sheet. Place something heavy, like a planet or a star, on it, and the sheet dips down. Now imagine little clocks sitting on different parts of that sheet. One is far away, in the flat part of space. Another is closer to the dip, down in the gravitational well. That second clock, it ticks more slowly, not because it's broken, not because of friction, but because gravity is stretching the fabric of time itself. And you might think, okay, that's kind of abstract, but does this actually happen? Oh yeah. Big time. In fact, it's been measured again and again. In 1976, scientists launched an atomic clock on a rocket and compared it to one on Earth. The clock up high, where Earth's gravity is slightly weaker, ran faster than the one on the ground. The difference was tiny, fractions of a second, but exactly what Einstein predicted. And here's the wildest part: you're experiencing this effect right now. If you're standing at the bottom of a mountain and your friend is up at the top, their watch is ticking faster than yours. Not enough to notice, unless you've got an atomic clock handy, but it's there. Gravity is stronger at sea level, so time is moving just a bit slower for you. This concept has a name: gravitational time dilation. And it's not just some cosmic curiosity, it's something we rely on every single day. Your GPS, for example, works because satellites orbit high above the Earth, where gravity is weaker and time runs a little faster. Their onboard clocks are actually adjusted to tick slightly slower than they normally would, so they stay in sync with clocks on Earth. Without Einstein's correction, GPS would be off by several kilometers every day. So yeah, relativity is literally helping you find your favorite coffee shop. But let's scale this up a bit. Imagine you're floating near a black hole. Remember, a black hole isn't just massive. It's the most extreme gravitational environment in the universe. Get close enough to it, and time slows to a crawl. A minute for you could be years for someone far away. That's not a metaphor. That's physics. It's not just a scene from Interstellar. It's real math, real spacetime, real time travel. And it forces you to ask, what is time really? If it can stretch, slow down, speed up, based on where you are, then it's not the universal, ticking clock we once imagined. It's not absolute. It's flexible, malleable, sensitive to the environment around it. Time is personal. And here's the philosophical side of it, the part that hits you at 2 a.m. You and I, we're not experiencing the same version of time. No two people are, ever. Your heartbeat, your aging, your thoughts, they're all running on your slice of spacetime. And the deeper you are in a gravity well, the slower your clock ticks compared to someone higher up, which means time doesn't just pass. It flows differently for everyone, depending on where you are. So next time you're out on a hike, or in a high-rise building, or flying on a plane, remember this: you're literally moving through time at a different pace than the people around you. And that difference, Einstein saw it coming. He saw that time could stretch, that it could be bent, that it could be pulled, just like space. And all of it comes from the simple, elegant idea that gravity isn't a force, it's a curve, a dip, a stretch in the invisible fabric of the universe. And you're just along for the ride. One heartbeat at a time. Space itself can expand. It sounds simple, but completely rewires how we think about reality. Space can stretch. Not like a rubber band. Not like something expanding into empty air. Space itself, this thing we walk through, float through, build galaxies in, can grow. Not just the things inside it, but the actual structure of the universe can expand. And it is. This idea didn't come from science fiction. It came from Einstein's equations. When he developed general relativity, he rewrote gravity from the ground up. Instead of being a force like Newton described, Einstein said gravity is the curving of spacetime itself. Big masses, like stars and planets, bend the space around them, and objects, including light, move through that curvature. But then he did something even bolder. He applied those same equations to the universe as a whole. And when he did that, the math gave him a surprise. It didn't want to describe a universe sitting still. It described a universe that was moving, either expanding outward or contracting inward. At the time, this didn't sit right with Einstein. The dominant belief back then was that the universe was static, unchanging, and eternal. So, instead of accepting what the math was saying, he tweaked it. He added something called the cosmological constant, a kind of repulsive force baked into space itself, just enough to hold everything in place and keep the universe from collapsing or expanding. It was a workaround, a mathematical band-aid to match what people believed the universe should be like. But then, in 1929, a guy named Edwin Hubble looked at the light from distant galaxies and noticed something strange. The galaxies weren't just drifting around. They were all moving away from us. And not only that, the farther away a galaxy was, the faster it was receding. This wasn't just motion. This was something bigger. The space between galaxies was getting bigger. It wasn't just that galaxies were flying through space. It was that space itself was expanding. Suddenly, Einstein's original equations, before he forced them to be static, made perfect sense. The universe wasn't frozen in time. It was dynamic, growing, and changing. Einstein famously called the cosmological constant his greatest blunder, because the truth was, his own theory had predicted a changing universe all along. So what does it mean for space itself to expand? It doesn't mean galaxies are pushing outward into some larger void. It means the fabric of the universe, the grid that everything sits on, is stretching. Imagine two dots on a balloon. When you blow up the balloon, the dots don't move on their own, but they get farther apart because the surface beneath them expands. That's our universe. The galaxies are like those dots, and the balloon. That's space. What's really expanding isn't the galaxies, but the space between them. Here's the mind-bending part. There's no center, no edge, no outside. The universe isn't expanding into anything. It's not inside a bigger container. Space isn't sitting in space. It is space. So when we say the universe is expanding, we're not talking about motion through some outer shell. We're talking about reality itself getting stretched, and it's not just a relic of the past. The expansion is happening right now, while galaxies form, while stars explode, while you're going about your day. The universe continues to grow, slowly, invisibly, relentlessly. In the 1990s, scientists discovered something that made this even more mysterious. They expected the expansion of the universe to be slowing down over time, because gravity should be pulling everything back together, right? But when they measured it, the opposite was happening. The expansion wasn't just continuing, it was accelerating. Something was making space stretch faster and faster over time. That something became known as dark energy, a mysterious force that seems to come from space itself. And guess what? It looks a lot like the cosmological constant Einstein had added and then discarded. Maybe it wasn't a mistake after all. And if all that wasn't weird enough, here's another question scientists still wrestle with: will this expansion keep going forever? Will space keep stretching until galaxies are so far apart they can't even be seen, until the night sky becomes dark and empty? Will the universe keep expanding until it tears itself apart? We don't have a final answer yet. But for now, the expansion continues. Silent, inescapable, all around us. And no, this doesn't mean everything is being stretched. Galaxies, solar systems, even atoms, you and I, aren't expanding. The forces that hold matter together are much stronger than the gentle tug of cosmic expansion. It only shows itself across huge distances, between galaxies, across vast gulfs of space. So next time you think about the universe, imagine it not as a still picture, but as a living structure, one where space isn't just the background, it's part of the story. Active, evolving, expanding. Einstein saw it first, in the quiet poetry of his equations. And ever since, we've been trying to understand just how far that expansion can go. The cosmological constant. Let's rewind to a time when scientists believed the universe was eternal, unmoving, always there, always the same. That was the vibe when Einstein was working on his theory of general relativity in the early 1900s. His equations were brand new, redefining gravity, space, time, everything. But then something unexpected popped out of that math. When he applied his equations to the whole universe, they didn't describe something still and peaceful. They described something unstable, something that either wanted to collapse in on itself or expand outward forever. And Einstein, he didn't like either option. So what did he do? He added a fix, a tiny term in his equations, just enough to hold the universe still. This new term was a kind of anti-gravity force, pushing things apart with exactly the right strength to balance out gravity, pulling things together. He called it the cosmological constant, and just like that, the universe was motionless again, on paper at least. It was a way of saying, okay, the math wants the universe to move, but let's just patch that up and make everything sit quietly. For years, this version of the universe held strong, because nobody had seen any reason to doubt it. But then came 1929. Edwin Hubble pointed his telescope at the sky and shattered that idea. Galaxies weren't standing still. They were moving away from each other. The universe was expanding, not because Einstein's cosmological constant was pushing it apart, but because space itself was stretching. Suddenly, the whole patch job, the balancing act Einstein had done, was unnecessary. And Einstein, being honest about it, called adding the cosmological constant the biggest blunder of his career. His original math, left alone, would have predicted an expanding universe before anyone else. He had been right all along and talked himself out of it. But here's where it gets interesting. Decades later, scientists were trying to figure out something else. Is the universe's expansion slowing down? Because gravity should still be pulling things back together, right? But when they measured distant supernovae in the late 1990s, they found the exact opposite. The universe wasn't just expanding, it was expanding faster over time. The expansion was accelerating. That discovery was a shock. It meant something was out there, some kind of energy, pushing the universe apart more and more. Scientists gave this mysterious force a name: dark energy. It seemed to be woven into the fabric of space itself. And guess what? The best way to describe it mathematically was to bring back Einstein's cosmological constant. The term he once erased became relevant again. This time, not to hold the universe still, but to explain why it's speeding up. It was no longer a mistake. It might be the key to understanding what's powering the expansion of the cosmos. So what is the cosmological constant? In simple terms, it represents the energy of empty space. Even a perfect vacuum, with no particles, no light, nothing at all, still has energy. And that energy pushes outward. The more space there is, the more of this energy you get, and the more expansion it causes. It's like a feedback loop as space grows. It brings with it more of this mysterious energy. And the more of that energy there is, the faster the universe expands, creating even more space in the process. The weird part, we have no idea why the cosmological constant has the value it does. If it were just a tiny bit stronger, the universe would have blown apart so fast that galaxies, stars, or life could never form. If it were weaker, gravity would have pulled everything back into a big crunch. But somehow, it's just right, balanced on a cosmic knife's edge, barely strong enough to pull galaxies apart over billions of years, but not too strong to destroy everything. It's one of the biggest mysteries in physics. Some scientists think the cosmological constant is a fundamental part of nature, something built into the very fabric of reality. Others think it's a placeholder, just the tip of a much deeper theory we haven't discovered yet. Maybe there's something beneath quantum physics that explains where this energy comes from. Maybe it's tied to extra dimensions or other universes. Or maybe the universe is just the way it is. No deeper reason. We don't know yet. But here's the full circle moment. Einstein's biggest mistake may have actually been a glimpse into the future. A term he added reluctantly, then threw away, is now central to how we understand cosmic acceleration. It shows how even in science, being wrong can lead you somewhere right. So today, the cosmological constant sits quietly in our equations again, not to keep the universe still, but to help us explain why it won't stop growing. It's a symbol of the strange poetry of physics. A small tweak in a line of math that turned out to describe the destiny of everything. The Equivalence Principle. Okay, imagine this. You're inside a sealed elevator, no windows, no way to see outside, and suddenly you feel yourself being pulled toward the floor. Are you standing on Earth, feeling gravity? Or are you drifting in deep space, with the elevator accelerating upward? There's no way to tell. That's the core of something Einstein called the Equivalence Principle, and it's one of the most profound ideas in physics. Einstein didn't come up with it out of nowhere. It all started with a strange little fact that puzzled scientists for centuries. If you drop a bowling ball and a feather, without air, they fall at the same rate. Their mass doesn't matter. In Galileo's time, this was already fascinating. But Einstein looked at it and asked a deeper question. Why does that happen? Why should an object's resistance to being moved, its inertial mass, be perfectly equal to its gravitational mass, the thing that feels weight? Those are two totally different ideas, right? But they always come out the same. That strange equality lit a fire in Einstein's mind, and then he had what he called the happiest thought of my life. He realized, if you're falling freely, like someone inside a dropped elevator, you don't feel your weight. You feel weightless. For you, in that moment, it's as if gravity vanished. And on the flip side, if you're in a spaceship accelerating upward at just the right speed, you feel a force pressing you into the floor. Just like gravity, these two situations, falling under gravity or accelerating in space, are indistinguishable. Gravity and acceleration are the same thing. This was revolutionary. Einstein realized that gravity wasn't a special, invisible pulling force like Newton imagined. It was something deeper. Something that could be replaced with motion. This idea became the foundation of general relativity. his grand theory that described gravity not as a force, but as the curvature of spacetime. Let's take a step back to really see how this works. Think of acceleration as the feeling you get in a car when you hit the gas. You're pushed back into the seat, right? Now imagine standing still on Earth. You feel the ground pushing up against your feet, what we call weight. According to Einstein, that pressure you feel is actually the same thing. You're being prevented from falling freely through curved spacetime. If the floor vanished beneath you and you fell, you'd feel weightless. Not because gravity disappeared, but because you're no longer being resisted. That's what makes the equivalence principle so powerful. It tells us that being in a gravitational field is locally the same as being in an accelerating frame. Not just metaphorically, not just as an analogy, literally the same in terms of physical experience and physical law. Here's a fun way to imagine it. Picture two scientists. One is deep in space, standing in a ship that's accelerating steadily. The other is standing on Earth. Both of them drop an apple. Both apples fall to the floor in exactly the same way. Both scientists measure the same behavior. Neither of them can tell, just from inside the room, whether they're feeling gravity or experiencing acceleration. That's how perfect the illusion is. And it's not just a philosophical idea. It leads directly to real, testable physics. It's why light bends around massive objects. It's why time runs slower near big gravitational fields. It's the reason GPS satellites have to account for time dilation, or your phone's maps would be totally wrong. Every prediction made by general relativity starts with this one realization: gravity is what you feel when acceleration is blocked. So here's the big idea: gravity isn't a thing pulling you down. It's the shape of space-time curving around mass. When you're standing still on Earth, what's really happening is that the planet is preventing you from following the natural path you'd take through spacetime. And that resistance, that push from the ground, is what you feel as weight. You're not being pulled down. You're being pushed up. Your feet are constantly resisting the fall you'd be taking if nothing were in your way. And if the floor wasn't there, you'd fall. And you wouldn't feel gravity anymore. You'd just be floating, free, natural, following the curves of the universe. The equivalence principle might sound simple, even obvious once you hear it, but it leads to one of the most complex and accurate theories in all of science. It tells us how planets orbit, how black holes form, why time can stretch or compress, all from the idea that falling is the same as floating and acceleration is the same as gravity. Einstein saw it first, not through some crazy experiment, but through a thought, a moment of quiet genius where he connected two everyday experiences and realized they were actually the same thing wearing different masks. And that changed the way we understand the entire cosmos. There is no preferred frame of reference. Okay, let's play a quick game. You're sitting in a smooth, quiet train. No bumps, no curves, no sound from outside. You toss a ball straight up, and it lands right back in your hand. Now here's the question: are you moving or standing still? You look around. Everything inside the train seems normal. The ball went up and down in a straight line. But here's the twist: you could be zooming at 100 miles per hour or just parked at a station. And there's no way to tell. This idea, that motion is relative, and there's no universal stillness to compare it to, is at the heart of something Einstein believed deeply. There is no preferred frame of reference. In simpler words, the laws of physics work the same no matter where you are or how fast you're moving, as long as you're not accelerating. And that idea, it changes everything. Now, this didn't start with Einstein. Way back in the 1600s, Galileo noticed it too. He said if you're in a ship moving smoothly across calm water, there's no experiment you could do below deck that would tell you whether you're moving or not. Drop something, throw something, watch the waves in your drink. It all behaves exactly the same whether the ship is in motion or not. Einstein took that idea and said, okay, what if that doesn't just apply to motion, but to light, time, and space themselves? And that's when things got really interesting. Let's talk about light for a second. For centuries, scientists believed that light, like sound, needed something to travel through. They called it the luminiferous aether, an invisible substance filling all of space. The Earth would move through this aether, like a boat through water, and we should be able to measure that motion. But in 1887, two scientists, Michelson and Morley, ran a famous experiment to detect the Earth's movement through this aether. The result? Nothing. Zero, no movement at all. It was as if light didn't care how fast you were moving or in what direction. That baffled scientists. But Einstein came in and said, maybe we've been looking at this the wrong way. What if light always travels at the same speed, no matter who's observing it? Even if you're flying toward it at half the speed of light or moving away from it, light still zips past you at the same exact speed. That goes totally against common sense. But if that's true, and it is, then space and time must be flexible. They have to stretch, squish, and warp just enough to make the speed of light stay constant. And that brings us back to frames of reference. A frame of reference is just a fancy term for your point of view, your coordinate system for measuring stuff like motion, distance, or time. You have your frame, I have mine. A rocket zooming by has another. And according to Einstein, no frame is more correct than any other. None of them are special. Not even the one where you feel like you're standing still. That sounds simple, but it leads to the weirdest consequences. Because if motion is relative, then so is time. If someone's moving fast compared to you, their time ticks more slowly from your point of view. Same with length. Objects shrink in the direction they're moving, as seen from your frame. And what's simultaneous in one frame might happen at totally different times in another, all because there's no cosmic scoreboard, no master clock, no central platform the universe uses to say, this is what's really happening. It's like this, you're floating in space. Another ship passes by at half the speed of light. You look at them and say, they're moving. But they look back and say, nope, you're the one moving. And you're both right. There's no background to measure against. No absolute rest, just motion, compared to something else. This principle is at the core of both special and general relativity. In special relativity, it tells us that all inertial frames, those moving at constant speeds, are equal. In general relativity, it gets even deeper. It says physics works the same in any frame, even if it's accelerating, spinning, or falling. That's how Einstein could treat gravity and acceleration as the same thing. No matter what your situation is, the laws of physics never change to suit your motion. So, why does this matter? Because it means reality itself is shaped by where you are and how you're moving, not just how fast you go, but how you measure time, distance, and even cause and effect. You don't just observe the universe. You're part of the perspective that defines how it works. There is no fixed grid out there. No center of the universe. No platform everything spins around. The universe isn't giving you some master key to unlock the one true view. Instead, it gives everyone their own ruler, their own clock, their own truth, and physics still works perfectly in all of them. That's the beauty of relativity. Not that it breaks the rules, but that the rules adapt to every perspective. It tells us that nature is fair. It doesn't pick favorites. No one gets the real view, and yet we can still all agree on the underlying reality, as long as we know how to translate between frames. It's like cosmic diplomacy. Everyone gets a seat at the table, and no one's perspective is more valid than another's. So next time you're sitting still, or speeding through the night on a plane, or watching a satellite orbit overhead. Just remember, you're not any more rest than anything else. You're just moving through your own frame. And the universe is cool with that. Energy has inertia. So we all kind of get the idea of inertia, right? It's that lazy resistance things have when you try to push them. Try shoving a parked car, and it doesn't budge. Push a shopping cart, and it rolls easily. That's inertia. Basically, the more mass something has, the more it resists changes in motion. But here's the twist most people never hear. Energy also has inertia. Yep, not just big heavy things. Not just matter. Even pure energy resists being pushed. Sounds weird at first, right? I mean, energy's not a thing you can hold. It's not a rock. It's not a planet. It's light, heat, movement, electricity. But in Einstein's world, energy and mass aren't two different things. They're two sides of the same coin. Remember his most famous idea: energy equals mass multiplied by the speed of light squared. Or as we all know it, energy equals mass times the speed of light squared. That one equation changed everything. It told us that mass and energy are interchangeable. You can convert one into the other. Matter can turn into energy. Energy can become matter. And in the right circumstances, they even behave exactly the same. So now let's go back to that idea of inertia. If mass resists acceleration, meaning it doesn't like to be pushed around, then anything with energy should resist acceleration too, because it has mass-like properties. That's what Einstein showed us: energy has inertia. And this isn't just a philosophical idea. It's real physics. Let's take light, for example. Photons, the particles that make up light, don't have mass in the traditional sense, but they carry energy, a lot of it. And they carry momentum, too, which means they can push things. Literally, shine a powerful enough laser onto a tiny mirror in space, and it'll move. That's the idea behind solar sails, using sunlight to push spacecraft across the solar system. The light doesn't have mass, but it has energy, and that energy pushes back, it resists, it interacts, it acts like it has mass. Want to hear something even more wild? The reason atomic bombs and nuclear power work at all is because of this relationship. When a small amount of mass is converted into energy, that energy doesn't just disappear. It retains the inertia of the mass it came from. The blast, the force, the heat, all that came from the inertia of something you couldn't even see before it exploded. It's like hidden weight inside the atom that reveals itself when you let the energy out. This idea even shows up in everyday physics. Imagine heating up an object, like, say, a metal rod. You pump energy into it, and it gets hotter. But not just hotter, it technically weighs more, only by a tiny amount. You'd never notice on a scale. But that thermal energy has mass now, and yes, that means the object has more inertia. It's slightly harder to move than it was when it was cold. Isn't that wild? Just by heating something up, you're increasing its resistance to acceleration, because you're increasing its energy. So why does this matter? Because it means energy is not just a concept. It's not some invisible bookkeeping thing that lives in equations. It's physical. It has presence. It pushes. It pulls. Energy affects how the world moves, and it responds when the world tries to move it. This is why we can't separate energy from the idea of mass or motion anymore. When you fire a rocket, you're not just burning fuel, you're releasing energy. And that energy has to go somewhere. It pushes the rocket forward, sure, but it also changes the rocket's inertia. The entire balance of motion, momentum, and resistance, all of it is shaped by how energy behaves. Einstein's vision was that all mass is energy in a tightly bundled form. So when you're pushing a box, or colliding particles at CERN, or even just heating a pan on the stove, you're interacting with a cosmic currency that underlies everything. Mass, motion, heat, light, they're all manifestations of energy. And that energy doesn't just sit still, it pushes back. So when we say energy has inertia, we're saying energy isn't passive. It behaves like something real and heavy. Something that doesn't want to move without a fight. Something that warps space, resists motion, and demands respect. And once you realize that, you start to see the universe not as empty space sprinkled with things, but as a sea of energy, constantly shifting forms. A place where everything that moves, heats, shines, or spins has weight, even when you can't see it. A unified field theory must exist. By the time Einstein had reshaped our understanding of space, time, gravity, and energy, you'd think he might have been satisfied, but not even close. Because for him, solving big puzzles wasn't just a job, it was personal. And there was one puzzle that haunted him more than anything else. How do we unify everything? You see, Einstein had this deep belief, a kind of unshakable faith, that nature isn't random or chaotic. He believed the universe is ordered, elegant, mathematically harmonious. And more than anything, he was convinced that all the forces in nature must come from a single, unified framework. That's what he called the unified field theory. One master equation that would tie together gravity, electromagnetism, and eventually everything else. It wasn't just a physics problem. It was a quest for meaning, he once said. I want to know God's thoughts. The rest are details. And what he meant by that wasn't religious. It was poetic. He wanted to know the ultimate law behind everything matter, light, fields, particles, time, space, all part of one single reality. But let's back up for a second. Einstein had already done something astonishing. He unified space and time into a single thing, spacetime. He showed that mass and energy are the same thing. And in general relativity, he did something no one expected. He showed that gravity is geometry, just the shape of spacetime. That was already unification on a massive scale. But then, there was this other force, electromagnetism. Electricity and magnetism were already known to be two sides of the same coin, unified by James Clerk Maxwell's equations in the 1800s. So now you've got gravity pulling things together, electromagnetism creating light and powering atoms. And Einstein believed those two must be connected, somehow. Deep down, they had to come from the same origin. But there was a problem. Gravity and electromagnetism are totally different beasts. Gravity is incredibly weak, but shapes the cosmos. Electromagnetism is insanely strong, but operates mostly at the atomic level. Gravity curves space-time. Electromagnetism uses fields. They don't speak the same mathematical language, or at least, they didn't seem to. Still, Einstein believed it was possible. So, after publishing General Relativity in 1915, arguably the most revolutionary theory of his career, he spent the rest of his life working on just one thing, unifying the fundamental forces. Day after day, year after year, he worked alone, slowly, quietly, and despite being one of the most famous people in the world, his ideas were mostly ignored in his final decades. Other physicists had moved on to quantum mechanics, this new, messy, probabilistic way of understanding the universe. But Einstein didn't trust it. It felt too chaotic, too disconnected. He believed quantum mechanics was incomplete, like a blurry photo of something deeper. And he was certain that a unified field theory, if it could be found, would explain not just gravity and electromagnetism, but maybe even quantum weirdness too. Now here's the sad part, Einstein never found it. He proposed many different versions of a unified theory, complex equations, exotic geometry, new dimensions, but none of them worked. None matched what we actually observe in nature, and in the end, he died in 1955 with a stack of papers beside his hospital bed, still scribbling out ideas, still searching. But here's what's amazing: even though Einstein never finished that puzzle, he started a movement that's still alive today. Physicists are still chasing unification, only now it's even more ambitious. Today we talk about the theory of everything. string theory, quantum gravity, loop quantum gravity, M theory. All attempts to do what Einstein dreamed of: bring all forces, gravity, electromagnetism, the strong and weak nuclear forces, under one roof. And it's not just about equations. It's about understanding the deep structure of reality. What is space really? What is a particle? What is information? Can gravity and quantum mechanics truly live together in one theory? And if they can, will that theory be beautiful, elegant, simple? Just like Einstein believed, even today, physicists are guided by Einstein's intuition, the idea that there must be a deeper unity beneath it all, that the chaos we see on the surface is just the messy edge of a more perfect truth. And even if we haven't found it yet, we keep looking. Because Einstein wasn't chasing math. He was chasing meaning. So next time you hear about black holes, or dark matter, or some new particle discovered at the LHCR, just remember, that's not noise. That's the universe whispering something. And somewhere inside it is the answer Einstein spent half a lifetime trying to hear: one truth, one equation, one unified field, and the hope that someday we'll understand everything. Spooky action is wrong or not yet understood. Let's talk about one of the most bizarre ideas in all of physics. An idea so strange, Einstein gave it the perfect nickname: spooky action at a distance. That was his way of saying, this can't be real. This has to be a misunderstanding. What was he talking about? Quantum entanglement. Now, if that word already sounds weird, yeah, it is. But let's break it down like you and I are just sitting on a couch figuring this out together. In quantum physics, particles don't behave like tiny billiard balls. They act more like clouds of probability, spooky little smears of maybe. They can be in multiple states at once, not here or there, but here and there, until you look at them. But it gets weirder, because sometimes two particles can become entangled, meaning they're somehow linked, even when they're separated by space. And here's where it breaks your brain. If you measure one of them, the other one instantly reacts, not gradually, not delayed, instantly, even if they're light years apart. It's like they're secretly talking to each other through a hidden channel faster than the speed of light. And for Einstein, that was a big no. He didn't just disagree with it. He refused to believe it could be the whole story, because it broke one of the rules he held sacred: nothing, no information, no influence, can travel faster than light ever. In 1935, Einstein teamed up with two other physicists, Podolsky and Rosen, and published a paper that's still famous today, the EPR paradox. Their point was this: if quantum mechanics says entangled particles can affect each other instantly, then either A, information is traveling faster than light, or B, quantum mechanics is incomplete, and there must be hidden variables behind the scenes that explain the connection. Einstein believed in option B strongly. He thought there had to be some deeper mechanism, some missing piece we just hadn't discovered yet, something beneath all the randomness, something local, predictable, and grounded in reality. Because for Einstein, the universe had to make sense. It had to be logical, continuous, causal. This spooky stuff, it smelled like magic, and Einstein didn't believe in magic. But here's the twist. After decades of debate in the 1960s, a physicist named John Bell found a way to test whether Einstein's hidden variables could exist or not. Bell's theorem basically said, okay, let's run an experiment. If reality really works the way Einstein wants it to, if those hidden variables are real, then we should see one set of results. But if quantum mechanics is right, we'll see something different. Fast forward a few decades. We ran the tests over and over again, and every time quantum mechanics won. The particles behaved exactly like the spooky predictions said they would. Entangled particles really do act instantly connected, no matter how far apart they are. Einstein's hidden variables theory pretty much ruled out, at least the kind he imagined. So was Einstein wrong? Kind of. But also, not completely. Because while quantum entanglement has been proven real again and again, we still don't fully understand it, and we still don't know what constant really means at the quantum level. Does it violate causality? Does it imply some kind of hidden, non-local connection across space? Is space itself even what we think it is? These are questions physicists are still wrestling with right now. Some modern interpretations say entangled particles are just two parts of one shared state, like they're not really separate to begin with. Others say information doesn't actually travel between them. It just looks like it does. And then there's quantum field theory, string theory, holographic principles, each adding a new twist to the puzzle. But Einstein's legacy in all this, it's not that he missed the mark. It's that he refused to settle. He challenged the popular idea. He poked at the weirdness. He asked deeper questions. And even though quantum mechanics has been unbelievably successful, there are still physicists today who think maybe Einstein wasn't wrong. Maybe he was just early. Because here's the thing, quantum mechanics works. But that doesn't mean it tells us the whole story. And just like Einstein believed in a deeper unity behind all the forces, maybe there's a deeper explanation behind quantum weirdness, too. So when you hear the words, spooky action at a distance, remember, it's not just a quirky phrase from an old physicist. It's the sound of someone brilliant saying, "This is weird, let's look closer." And that curiosity, that need to go beyond the surface, is what drove Einstein his whole life. Not to deny the weirdness of nature, but to understand it fully, elegantly, deeply. Particles don't just pop out of probability. You're watching an empty stretch of space. No particles, no fields, just silence. And then, out of nowhere, pop, a particle appears, not because something triggered it, not because it was caused by anything, just because it could. Welcome to the world of quantum probability. See, in the quantum universe, particles don't behave like little marbles. They aren't sitting there in well-defined places, doing predictable things. Instead, they exist as probability waves, clouds of maybe, scattered through space. And when we measure them, boom, the wave collapses. The particle appears. It's like the universe makes up its mind on the spot. According to the standard quantum model, this randomness isn't just a matter of not knowing something. It's not like flipping a coin and not seeing the result. It's deeper than that. It's saying the coin doesn't have a result until you look. There is no outcome until the observation happens. Einstein hated this deeply. He wasn't against quantum theory entirely. After all, his work on the photoelectric effect helped create it. But he could never accept this part of it, this idea that reality is fundamentally probabilistic. To him, that wasn't science, it was surrender. He once said, "God does not play dice with the universe." And let's be clear, he didn't mean God in a religious sense. Einstein saw God as a metaphor for the deep structure of nature, logical, ordered, elegant. He believed that beneath the fuzziness of quantum mechanics, there had to be a deeper level of reality. Something deterministic, something hidden, something that explained why a particle ends up here and not there. Why this happened instead of that. In Einstein's view, the particle was always somewhere. We just didn't know where. It wasn't created by observation. It didn't pop out of possibility. It existed independently. And probability was just a tool for dealing with ignorance, not a fundamental law of the cosmos. But quantum mechanics had other ideas. Niels Bohr, one of the founding fathers of quantum theory, famously clashed with Einstein on this. Bohr believed nature is probabilistic. That randomness isn't a flaw, it's a feature. To Bohr, trying to peek behind the curtain of quantum uncertainty was like asking what's north of the North Pole. The question just didn't make sense. Einstein disagreed, passionately. In the 1930s, he started proposing thought experiments, mental tests designed to expose the flaws in quantum theory. One of his most famous was a challenge to the uncertainty principle, the idea that you can't simultaneously know both the position and momentum of a particle with perfect accuracy. Einstein kept asking, what if we could? What if we're just missing part of the picture? What if quantum mechanics is like a shadow, a blurry projection of a sharper, deeper reality? He spent decades trying to prove it, digging for hidden variables, deeper equations, a better map, but he never found it. And as the 20th century rolled on, quantum mechanics kept succeeding. Its predictions were astonishingly accurate. It explained chemistry, electronics, nuclear reactions, semiconductors, lasers. It worked. So most physicists moved on. They stopped worrying about the why and focused on the what. But Einstein never let go. And here's where it gets really fascinating. Even though modern experiments have confirmed the predictions of quantum randomness again and again, especially through Bell's theorem, which ruled out a whole category of hidden variable theories, there are still physicists who agree with Einstein's instinct. They think the quantum model is incomplete. That it works, yes, but it doesn't explain why, and it doesn't tell the full story. Some modern interpretations of quantum mechanics, like Bohmian mechanics, actually bring determinism back. They suggest that particles do have real paths, and that something deeper hidden in the fabric of the universe is guiding them. Others, like the many worlds interpretation, say that every possible outcome actually does happen in some branch of the universe. So nothing pops out of probability, it just plays out across infinite realities. Wild, right? But here's the heart of it. Einstein couldn't accept that reality itself was undecided, that the most fundamental level of nature was a coin toss. He believed in something deeper, something elegant, cohesive, real. Not vague probabilities, but actual causes. Not particles springing into existence out of math, but laws driving their behavior, laws we just haven't fully uncovered yet. So when we say particles don't just pop out of probability, we're channeling Einstein's voice, his challenge, his refusal to accept a universe ruled by chance. And whether he was right or wrong, that refusal still echoes through every new experiment, every new theory, every physicist who thinks, wait a second, what if there's more? God doesn't play dice. It's one of Einstein's most quoted lines. You've probably heard it before, even outside of science. But what did he really mean by that? Was he talking about religion? Faith? Divine control? Not at all. Einstein wasn't defending belief in a personal God. What he was really talking about was the laws of nature. Let's go back for a second. By the time Einstein was in the second half of his career, quantum mechanics was rising fast. It was flashy, new, weird, and most importantly, it worked. It could explain the behavior of atoms, electrons, photons, things classical physics just couldn't touch. But at the heart of quantum mechanics, there was this idea uncertainty. Not just, we don't know, but you can't know. Not fully, not even in principle. Take the Heisenberg uncertainty principle, for example. It says you can't measure both the position and the momentum of a particle with complete accuracy. The more precisely you know one, the fuzzier the other becomes. Now, to a quantum physicist, that's not a problem. It's just how the universe works. But to Einstein, that wasn't a law of nature. That was a sign something was missing. And that's where the dice come in, because quantum mechanics doesn't just deal with probabilities as a tool for estimating things. It bakes them right into the structure of reality. It says, fundamentally, the outcome of a quantum event isn't determined until it happens, until you observe it. It's like nature rolls the dice and then decides what reality looks like. Einstein could never accept that. He believed nature was too elegant, too structured, too unified to be built on randomness. In his words, the old one, his nickname for the universe or the laws of nature, is subtle but not malicious. In other words, the universe may be complex, but it isn't playing tricks. What Einstein wanted, what he needed, was a universe that was ultimately deterministic, one where everything, even the strangest quantum effects, had causes behind them. He thought quantum mechanics was correct in its predictions, but incomplete in its explanation, that there were hidden variables, deeper layers of reality we hadn't uncovered yet. Something beneath the probabilities, something real. The thing is, Einstein wasn't trying to be difficult. He wasn't just holding on to old ideas for no reason. He was consistent. From the beginning of his career, he believed the universe followed patterns. Subtle, yes, but logical. Relativity itself was built on that belief that even if time and space were flexible, the laws of physics remained consistent for everyone. So why should we suddenly accept randomness at the deepest level? Why would the rules stop making sense just because we're zooming in? Niels Bohr, the great champion of quantum theory, had a very different take. He believed Einstein was clinging to classical ideas that just didn't apply anymore. And their debates were legendary, long, technical, sometimes even a little snarky. Bohr would say, "Stop telling God what to do." Einstein would shoot back with another thought experiment trying to poke a hole in quantum logic. One of their arguments revolved around whether reality exists when it isn't being measured. Quantum mechanics seemed to suggest no, it doesn't, that a particle only takes on definite properties when observed. Einstein's response: "I like to think the moon is there even if I'm not looking at it." That might sound poetic, but it's also deeply philosophical. For Einstein, reality was objective. It existed independently of our measurements or awareness, and any theory that said otherwise, no matter how successful it seemed, had to be missing something important. Over time, as experiments kept proving quantum mechanics right, the physics world began to move on. Einstein's resistance was seen as stubborn, brilliant, but outdated. But here's the twist. Even now, nearly a century later, we still don't really understand why quantum mechanics works. We can use it. We can build lasers and transistors and quantum computers with it. But the why behind it, the deeper logic, still up for debate. And some physicists today are once again asking, was Einstein onto something? Maybe not in the details, but in the instinct. That nature has layers we haven't peeled back yet. That this isn't the end of the road. That there's a deeper order beneath all this quantum chaos. Because here's the truth: physics is about more than equations. It's about the stories we tell ourselves about the universe. And Einstein's story, his refusal to believe that randomness rules the cosmos, has never really gone away. It still lives in every scientist who asks the harder question, who digs a little deeper, who says, this explanation works, but is it right? So next time you hear the phrase, God doesn't play dice, don't take it as dogma, take it as defiance. The kind of defiance that built relativity, that questioned every accepted truth, that looked at the universe and said, there's more, and I'm going to find it. The universe is understandable. You ever look up at the night sky and just feel overwhelmed? All those stars, light that's taken millions of years to reach your eyes, galaxies stacked behind galaxies, endless distances, the sheer size of it, it makes you feel small. Now imagine this: in the middle of all that chaos, all that immensity, you, a human being on a tiny blue planet, can actually understand how it all works. That idea, that belief, Einstein was obsessed with it. He once said, the most incomprehensible thing about the universe is that it is comprehensible. It sounds like a paradox, but it's not. It's a celebration, because Einstein didn't think the universe was cold or random or inaccessible. He believed it was intelligible, that its laws could be discovered, its patterns revealed. its logic decoded, and not by gods or angels or machines, but by us humans, thinking, questioning, wondering. To Einstein, that wasn't just a coincidence. It was something sacred. He believed the universe was structured in such a way that the human mind could actually make sense of it. That our brains, these little bundles of neurons evolved over millions of years, had the power to uncover the deep mechanics of reality. Not just to guess at them, but to know them. And he wasn't naïve about how hard that would be. He knew nature was subtle, complex, sometimes deceptive. But he also believed something fundamental, that if we ask the right questions, if we're patient enough, the answers are there. They're built into the fabric of the cosmos. Einstein's life was a testimony to that belief. Think about it. He started with a simple question: what would it be like to ride alongside a beam of light? And that childlike thought experiment led to special relativity, an entirely new way to understand space and time. A few years later, he wondered about a man falling off a roof and ended up revolutionizing gravity with general relativity. These were massive world-shaking theories, but they were born from curiosity, from faith in the order of the universe. And here's the thing: Einstein didn't believe the universe was understandable because we're smart. He thought it was understandable because it was designed that way, not by a designer in the religious sense, but by something deeper, a kind of logical elegance baked into reality itself, a coherence, a unity, a simplicity behind the complexity. To him, that was the ultimate goal of science: to find the beautiful, simple principles that could explain everything. And he wasn't alone in this. Many of the greatest physicists in history have echoed the same feeling, that the universe isn't just a chaotic mess of particles bouncing around. It's a cosmic puzzle. And we have the pieces. The trick is figuring out how they fit together. Einstein believed those pieces would eventually form a complete picture. That there was, somewhere out there, a unified theory that could explain every force, every particle, every interaction. Something that ties together gravity and electromagnetism and quantum behavior into one seamless framework, not a patchwork of approximations, but a deep, elegant whole. He spent the last decades of his life searching for it. He never found it, but he never stopped looking. Even when quantum mechanics challenged his worldview, even when others told him to just accept the uncertainty, he refused. Not because he didn't respect the science, but because he believed the universe made too much sense to leave it at randomness and probability. There had to be more. You see, for Einstein, science wasn't just about calculation. It was almost spiritual. He saw the universe as a vast, mysterious cathedral, and physics was the act of walking into it, quietly, reverently, trying to read the blueprint. He didn't care about equations for their own sake. He cared about what they revealed, what they meant. That's why he also believed science and philosophy couldn't be separated. He thought deeply. He questioned assumptions. He wanted to know not just how things worked, but why. And that mindset, the slow, careful, contemplative one, is what led him to some of the biggest breakthroughs in human history. So what does it mean to say the universe is understandable? It means there's a pattern beneath the chaos, a code beneath the surface. It means nature doesn't just act. It follows rules. And those rules aren't locked away behind a cosmic firewall. They're discoverable, with thought, with effort, with imagination. That's what Einstein believed, and honestly, it's kind of comforting. Because in a world that can often feel unpredictable, even meaningless, there's this quiet truth humming underneath everything the universe wants to be known. It invites us to explore it, to question, to observe, to understand, not because we're special, but because the very structure of reality rewards curiosity. So when we look up at the stars, when we read books on physics, or wonder how gravity works, or ask what happened before the Big Bang, We're not just playing mental games. We're doing what Einstein believed we were made to do. We're trying to understand the universe, and he believed without a doubt that we can. No action at a distance in nature. You flip a switch on Earth and instantly, something happens on the far side of the galaxy. No signal, no delay, no connection in between. Just action and result. That kind of thing might sound like sci-fi magic, but it's also what some interpretations of quantum mechanics seem to allow. Einstein, he hated it. To him, that idea violated one of the deepest rules of how the universe should work. He called it spooky action at a distance, and he believed it just couldn't be real. So what's this all about? It starts with something called locality, a basic principle Einstein held sacred. Locality says that objects can only affect each other if something connects them. A force, a field, a wave, and whatever that something is, it can't move faster than the speed of light. It's like a rule of cosmic etiquette, no instant messaging across the universe. But here's where it gets tricky. In the world of quantum physics, there's something called entanglement. When two particles are entangled, they share a strange connection. So strange that when you measure one of them, the other immediately responds. Doesn't matter how far apart they are. Could be inches, could be light years. Measure one, and the other seems to. No signal, no delay. Just instant correlation. That's where Einstein threw up his hands. He didn't deny the math. He didn't deny the experiments. What he denied was the interpretation. He believed there had to be something missing, a deeper layer of physics, some kind of hidden mechanism that restored locality and causality. Because to Einstein, nature doesn't cheat. It doesn't pull invisible strings from across space. It doesn't let particles talk without a medium. And it definitely doesn't allow instant effects without something in between. In 1935, Einstein, along with colleagues Boris Podolsky and Nathan Rosen, published a paper. It's known today as the EPR paradox. The point of it was simple: if quantum mechanics was complete, then it had to allow this kind of instant, non-local behavior. But if that was true, then quantum mechanics violated one of the most basic principles of relativity. Their conclusion: quantum theory couldn't be the final word. There must be hidden variables, something deeper that preserved locality. For decades, physicists debated this. Some sided with Einstein, hoping for a more realistic explanation of quantum weirdness. Others leaned into the strangeness, arguing that maybe nature really is that weird. And then came the big twist. In the 1960s, a physicist named John Bell devised a test, now known as Bell's theorem. It basically said, if Einstein was right, and there were hidden variables preserving locality, then certain patterns would appear in experiments. But if quantum mechanics was right, if entanglement really did allow spooky action at a distance, then different patterns would show up. It was testable. And when scientists finally did the tests, quantum mechanics won. Time after time, experiment after experiment, the results matched the predictions of entanglement. No local hidden variables, no classical explanation, just weirdness. Confirmed. Nature, it seems, does allow instant correlations. No signal, no in-between, just spooky action. But here's the catch: even today, we're still arguing about what that actually means. Does it mean information travels faster than light? Most physicists say no, it's not a communication channel. Does it mean the universe is deeply non-local? Maybe. Or maybe our entire framework for space and time is missing something even deeper. And that's where Einstein's stubbornness still resonates, because even if he was wrong about quantum entanglement, his deeper concern, his demand that physics make logical, causal sense, is still valid. He wasn't afraid of new ideas, but he was wary of explanations that asked us to abandon the principles that made physics work in the first place. To him, no action at a distance wasn't just a preference. It was a safeguard against magical thinking, against turning science into mystery without mechanism. You could say Einstein lost that argument. But in another way, he framed the entire conversation. He forced physicists to clarify what they meant, to test what was testable, to distinguish between what we observe and what we understand. And that legacy matters, because the questions Einstein raised about the reality of entanglement, the nature of space and time, the role of causality, still drive research today. They push us to ask not just what happens, but why. What's underneath? What's really real? So even though quantum entanglement may be here to stay, and even though action at a distance might be part of nature after all, Einstein's refusal to accept it blindly wasn't a mistake. It was a challenge, a demand for clarity, a call to keep searching until the logic reveals itself. Because in Einstein's universe, nothing happens without a reason. And if something looks like it does, then we just haven't looked deep enough yet. Gravitational waves exist. Let's start with something simple. Imagine you're floating in space, totally still, totally quiet, no wind, no sound, just you suspended in nothing. And then, without warning, space itself ripples around you. Not air, not a sound wave, not even light. Space is moving. That's what a gravitational wave is. A tiny ripple in the actual fabric of spacetime, born from the most violent events in the cosmos, traveling billions of years through nothing and gently, subtly, passing through you. Now rewind back to 1916. Einstein had just finalized his theory of general relativity, and buried deep in the math was a weird possibility that accelerating massive objects, like, say, orbiting stars or colliding black holes, could create waves in spacetime. Not metaphorical ones, literal ones, like the way a rock disturbs water, except this is spacetime itself that ripples. Einstein wrote about it. The equations said it should be real. But still he wasn't fully convinced, because these waves would be absurdly small. Even the biggest ones would stretch or squish space by less than the width of a proton. He figured sure, they might exist, but we'd never detect them. Too faint, too subtle, too buried in cosmic noise. And for nearly 100 years he was right. Gravitational waves were the unicorns of physics, predicted but never seen. We had indirect hints. We saw binary stars losing energy exactly the way gravitational radiation would predict. But a real direct detection, nothing. Until one quiet morning in September 2015, two black holes, each about 30 times the mass of the Sun, were spiraling toward each other. They had been dancing this death spiral for aeons, getting closer, spinning faster. And then, in a fraction of a second, they collided. Boom. In that final moment, they released more energy than all the stars in the observable universe combined. And a ripple spread out across space. That ripple reached Earth, and we caught it. The signal was picked up by LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO isn't a telescope. It doesn't use mirrors or lenses. It's basically two enormous L-shaped arms 4 kilometers long, firing lasers down each side. The idea is simple in theory but wildly precise in practice. If a gravitational wave passes through, it slightly distorts space itself, making one arm just a tiny bit longer or shorter than the other. The lasers detect that difference. And that's exactly what happened. On September 14, 2015, LIGO recorded a blip, a tiny, rising chirp. It matched perfectly with what a pair of merging black holes would produce. And just like that, gravitational waves were no longer a theory. They were real. Einstein's century-old prediction, confirmed by instruments he could never have imagined. And that moment, it changed everything. Because gravitational waves aren't just a cool trick of math, they're a new sense. For 100 years, astronomy relied on light. Visible light, radio waves, X-rays, gamma rays, it's all just different forms of light. But light has limits. It can be blocked, absorbed, distorted. Gravitational waves don't care. They move through stars, galaxies, gas clouds, everything. They carry pure information about the most extreme events in the universe. Black holes, neutron stars, cosmic collisions. And now, for the first time, we can hear them. Since that first detection, we've heard more. Dozens of events. Black holes smashing together, neutron stars spiraling inward and exploding in a flash of light and gravity. Each one gives us new insights about matter, about space, about time. And think about this. Einstein himself wasn't sure we'd ever catch one. But now we're not just catching them. We're building a gravitational map of the cosmos. And this is just the beginning. New detectors are being built. Sensitivity is increasing. Soon we'll be able to detect smaller waves, older waves, maybe even primordial ones, echoes from the birth of the universe itself. We're not just looking at space anymore. We're listening to it. Like dropping the needle on a cosmic vinyl. Gravitational waves prove something Einstein believed deeply, that the universe isn't still, it's alive with motion and transformation. Even the most distant, catastrophic, unimaginable events leave behind a trace, a ripple, a whisper. And now we can hear it. What was once just a strange prediction in Einstein's notebook is now a brand new way to experience the cosmos. And who knows, maybe one day those waves will tell us something we never expected, something deeper than light could ever show. Photons are discrete quanta of light. You know how sometimes something feels so obvious that nobody questions it. That's how light used to be. Everyone just kinda agreed. Light was a wave. Like sound, like ripples across water. You could measure its frequency, its wavelength, and how it bends and bounces. No mystery there. Done and dusted, until it wasn't. See, around the turn of the 20th century, scientists were playing around with this thing called the photoelectric effect. It sounds fancy, but the idea is pretty straightforward. Shine light on a metal surface, and under the right conditions, electrons get kicked out. Light hits the metal, electrons pop out. Cool, right? But the deeper they looked, the weirder it got. Now, here's where classic physics should have had the answer. If light is just a wave, then brighter light, more intense waves, should transfer more energy. It should knock out more electrons, right? Just like stronger ocean waves hitting a beach with more force. But here's the twist, it didn't. Scientists tried this over and over again. No matter how bright the red light was, it just wouldn't knock out any electrons. Even when they cranked up the intensity to insane levels. Still nothing. But then they'd shine even a dim beam of ultraviolet or blue light, and boom. Electrons came flying out instantly. It was like physics was playing favorites. And it made zero sense. That's where Einstein stepped in. And he wasn't afraid to flip the script. He proposed something radical. Maybe light wasn't just a wave. Maybe it could behave like a particle too, a kind of energy bullet, not a continuous stream, but delivered in individual packets, and he called those packets quanta of light. Today, we know them as photons. Here's the key: every photon carries a specific chunk of energy. That energy depends on the frequency of the light. Higher frequency, more energy per photon. So blue light has high-frequency photons, red light, much lower. And that explained everything. It wasn't about the brightness of the light. It was about the energy of each individual photon. If a photon didn't carry enough energy, it couldn't knock out an electron. No matter how many of them you threw, imagine trying to knock over a bowling pin. You could throw 1,000 ping-pong balls at it, and nothing would happen. But one baseball, that'll do the trick. That was Einstein's genius. He looked at a strange little experimental hiccup and realized it meant our whole picture of light was incomplete. Light wasn't just waves. It also came in particles, little bursts, discrete quanta. This wasn't just a clever fix. It was a paradigm shift. It meant that energy itself, something we always thought of as smooth and flowing, actually came in chunks, like pixels on a screen. like stairs instead of a ramp. This idea didn't just explain the photoelectric effect. It cracked open the door to quantum mechanics, one of the most successful and mind-bending branches of physics we've ever discovered. And here's a fun twist: this idea, the thing that helped kickstart quantum theory, that's what Einstein won the Nobel Prize for. Not for relativity, not for bending space or slowing time. It was this, the photoelectric effect. Now here's where things get even trippier. Because once we accepted that light could act like a particle, we had to reconcile something very strange. Light still behaved like a wave in other experiments. It could interfere with itself. It could diffract, bend, ripple. But it also arrived in discrete hits, photons, like little bullets. So which is it? A wave or a particle? The answer: both. It depends on how you look at it. If you design an experiment that asks a wave-like question, light answers like a wave. If you ask a particle-like question, it responds like a particle. This is called wave-particle duality, and it applies not just to light, but to matter itself. Even electrons do this. Let that sink in for a second. Our universe, at its most fundamental level, doesn't always behave in a way we can visualize. It doesn't always let us put things into neat little categories. Light isn't just this or that. It's both and neither. It's quantum. And here's the deeper magic: photons aren't just quirky little energy packets. They're massless. They travel at the ultimate speed limit, what we call the speed of light, and they never, ever slow down. Not even a little. They're responsible for everything from vision to solar power to the glow of the stars. When you look around you, everything you see is photons bouncing off stuff and hitting your eyes. Photons let us see the universe, but they also let us study it, manipulate it, build with it. We use them in fiber optic cables, in lasers, in medical imaging. We even use them in quantum encryption, where a single tampered photon can reveal an eavesdropper. And here's the kicker. This whole idea, photons, light as particles, quantum energy packets, it started because a young Einstein wasn't satisfied with the answer everyone else accepted. He saw something strange. And instead of brushing it off, he asked, what if we're missing something? Turns out we were. And that question didn't just explain a weird experiment. It opened the door to a whole new reality. Motion can only be measured relatively. Let's start with something so basic it feels almost too obvious: motion. If you're walking down the street, you'd say you're moving. If you're sitting on a bench, you'd say you're still. Simple, right? But here's the twist: Einstein would probably raise an eyebrow at both of those answers. Because in the universe he described, motion isn't an absolute thing. There's no cosmic referee yelling, "Yep, you're officially moving," or "Nope, you're still." In Einstein's world, motion can only be measured in relation to something else. Let's break this down. Say you're sitting in a super smooth train. No bumps, no sound, just silence. The blinds are drawn, so you can't see outside. You toss a ball straight up, and it comes right back down into your hand, like you're sitting at home. So are you moving? From your perspective, no. Everything feels still. But what if that train is quietly gliding at 300 kilometers an hour? Now here's the catch: you wouldn't know unless you looked outside. Your ball still goes up and down the same way. Your coffee stays in your cup. Nothing changes inside the train. And this isn't just a neat trick. It's a deep truth of physics that goes all the way back to Galileo. He was the first to point out that the laws of motion behave the same whether you're on a moving ship or standing on dry land. He called this the principle of relativity. Einstein didn't invent this idea, but he took it way further. In 1905, he dropped a bombshell: the laws of physics are the same in all constant speed reference frames. Not just ships and trains, but anything moving in a straight line without acceleration. That includes a spaceship blasting through space at 90% the speed of light, or you just chilling in your kitchen. As long as you're not speeding up or turning, physics treats you the same. And here's where things get wild. That means there's no such thing as absolute motion. No master coordinate grid in space. No background stage that tells us who's really moving and who's not. It's all about perspective. Let's say you're on Earth watching a spaceship zoom by at an insane speed. From your point of view, it's definitely moving. But flip it, the astronauts on board feel totally stationary, and from their perspective, you're the one speeding past. So, who's right? Both. There's no preferred answer. In Einstein's view, every frame of reference is equally valid. There's no cosmic center of motion, no universal stillness. Just a bunch of things moving relative to other things. And this idea, this relativity of motion, isn't just theoretical. It's the foundation of modern physics. It's what leads to all those strange effects you hear about in relativity. For instance, when you move really fast, time slows down for you. This is called time dilation. And from your perspective, it's the rest of the world that's lagging behind. Or how length contracts along the direction of motion. A spaceship traveling near the speed of light would actually appear shorter to a stationary observer. But the people on board, everything feels normal. Even mass increases as you accelerate, though only from the viewpoint of someone watching you move. Again, it's all about where you're looking from. All of these effects happen because motion is relative. There's no absolute. You are here at rest, marker in the universe. Your experience of space and time depends on how you're moving compared to someone else. This isn't just philosophical musing. It's baked into real-world tech. Ever used GPS? Those satellites above Earth are moving fast, and they're farther from the planet's gravity well. Time actually ticks differently for them than it does for us on the ground. Engineers have to account for both special and general relativity when designing GPS systems. If they didn't, your location would drift by kilometers a day. So yeah, your Uber arriving on time owes a debt to Einstein's insights about relative motion. But let's zoom out from the tech and get a little deeper. What Einstein really destroyed with this idea is our craving for a fixed stage the universe plays out on. Newton believed in something called absolute space, a kind of invisible framework that everything moved within. Even if there was no matter in the universe, Newton thought space itself would still exist, quietly waiting. Einstein said nope, no empty stage, no universal clock, no privileged observer, just relationships between things, one thing moving compared to another. Even time, the most constant thing we think we experience, becomes flexible in Einstein's hands. There's no single now that everyone shares. If you and I are in motion relative to each other, our versions of what counts as no are different. What's happening for you might already be in my past, or not yet in my future. And that idea, that's not science fiction. It's real. It's measurable. It's been tested over and over with atomic clocks on jets, satellites, and particle accelerators. Everything we know, from space exploration to quantum communication, relies on this principle. There's no such thing as absolute motion, only relative motion. So next time you're sitting in a plane, watching the clouds drift by, ask yourself, who's really moving? You. The Earth? The sky? In Einstein's universe, the only answer that matters is compared to what? Mass tells space how to curve, and space tells mass how to move. Let's throw out everything you thought you knew about gravity for a second. We've been taught, since we were kids, that gravity is a force, that it pulls things down, like some invisible hand grabbing apples off trees and astronauts back to Earth. You drop a pen, and gravity pulls it to the ground. But what if that's not what's actually happening at all? What if gravity isn't a force at all, but a kind of geometry? a bending, a warping, a curve in the very fabric of reality. That's exactly what Einstein proposed. He didn't just tweak Newton's laws. He rewrote the entire way we think about space and time. Here's how he put it. Mass tells space how to curve, and curved space tells mass how to move. Let's break that down, piece by piece. Imagine a giant rubber sheet stretched out tight, like a trampoline. That's our space. Now, take a bowling ball and set it down in the center of that trampoline. What happens? It sinks in, right? The rubber dips. It curves. Now take a small marble and roll it across the sheet. As it passes near the bowling ball, its path bends, not because the bowling ball reached out and pulled it, but because the sheet itself is no longer flat. This is Einstein's vision of gravity. That rubber sheet, that's spacetime, the combined fabric of space and time itself. The bowling ball, that's mass, like a star or a planet or you. And the marble, that's anything else moving through space, from satellites to light itself. So, when Einstein said mass tells space how to curve, he meant that anything with mass, even you, even your phone, deforms the fabric of space around it. The more massive the object, the deeper the curve, and space tells mass how to move. That's the second part. That curvature is what guides the motion of other objects. Things follow the shape of spacetime, moving along the curves like marbles following dips in that rubber sheet. And this model of gravity, it works. It predicted things Newton's theory never could, like how Mercury's orbit is just slightly off from what Newton's gravity predicted. People thought maybe there was another tiny planet messing with its orbit. But Einstein's curved spacetime nailed the math exactly. And light doesn't have mass. So under Newton's model, it shouldn't be affected by gravity at all. But Einstein said, hold on, even though light has no mass, it still travels through spacetime. So if spacetime is curved, light should follow that curve too. And guess what? In 1919, during a solar eclipse, scientists observed light from distant stars bending around the sun. Exactly as Einstein had predicted. That was the moment general relativity went from wild theory to revolutionary fact. Suddenly, gravity wasn't some mysterious invisible force acting at a distance. It was geometry. Now, let's take this even further. Because if space can be curved, then so can time. In Einstein's theory, space and time are two sides of the same coin, a unified fabric called spacetime. So when you curve space, you also curve how time flows. That's why time runs slower near massive objects, like black holes or even just Earth. It's not just some side effect. It's because the shape of spacetime is different in strong gravitational fields. Time itself gets stretched. Think about that for a second. Gravity is literally bending your seconds, and the deeper you are in a gravity well, like near a planet or star, the slower your clock ticks compared to someone farther away. It's not just theory either. We've tested this with high-precision atomic clocks placed at different altitudes. The clock closer to sea level, slightly deeper in Earth's gravity, ticks ever so slightly slower than one up in the mountains. So yes, you technically age a teeny bit slower at the beach than you do on a mountaintop. Thanks, gravity. Now let's take this idea to its most extreme: black holes. If enough mass gets crammed into a small enough space, it curves spacetime so dramatically that nothing, not even light, can escape. That's a black hole. It's not a hole in space. It's a pit in the fabric of spacetime so deep that it's essentially sealed off from the rest of the universe. It's not pulling things in with some mysterious force. It simply shaped spacetime so steeply that everything falls in. And yes, Einstein's equations predicted black holes. He didn't like them at first. Even thought they might be mathematical artifacts. But the math said they were real, and decades later we found them. So when we say mass tells space how to curve, and space tells mass how to move, we're not being poetic. That's the literal truth of how gravity operates in Einstein's universe. It's why planets orbit stars. Not because stars are pulling them in, but because the stars are denting the space around them, and the planets are rolling along that curved path. It's why galaxies form and spiral the way they do. It's why light bends, why time stretches, why clocks tick differently depending on where you stand. All of it, because spacetime is not flat, and gravity isn't pulling you. It's just guiding you along the path that space is already laying out, so next time you feel gravity holding you down, don't think of it as a force gripping you. Picture it as space itself gently curving beneath your feet. Reality exists independent of observation. So here's a wild idea that still stirs up debates today. Does something exist even if no one's looking at it? Like, if a tree falls in the forest and there's absolutely no one around, no people, no cameras, not even a squirrel, does it actually fall? Or better yet, does it even exist? You might laugh and go, obviously, yeah. The tree's not waiting on me to check in before it lives its tree life. But here's where things get weird, and where Einstein, once again, found himself staring down the rest of the scientific world. Because in the early 20th century, quantum mechanics burst onto the scene, and it brought with it this totally strange and honestly unsettling idea that reality doesn't decide what it is until you measure it. Let's take the famous double-slit experiment. It showed that particles like electrons and photons, little bits of matter and light, behave like waves when you're not looking at them. But the moment you observe them, they collapse into particles. They pick a position, they settle down, like they knew they were being watched. It's not just spooky, it's almost philosophical. According to one interpretation of quantum physics, before you make a measurement, a particle isn't really anywhere. It exists in a superposition, a blend of all possible states, and it's only when you observe it that it chooses a state. Einstein hated that. He wasn't being stubborn. He just deeply believed in something that, to him, was fundamental to science, that reality exists independently of observation. In other words, the moon is still out there even if nobody's looking at it. The laws of physics keep doing their thing, whether we're watching or not. He saw quantum mechanics as a brilliant theory. He admired its precision, its usefulness. But he felt it couldn't be the complete picture. Because any theory that says, we don't know what's real until we measure it, sounded to Einstein like giving up on the whole point of physics. To describe a universe that exists on its own, governed by laws, not by what we decide to observe. Let's take a concrete example in quantum mechanics. You can't know both the position and momentum of a particle with perfect accuracy at the same time. This is Heisenberg's uncertainty principle. It's not because our instruments aren't good enough. It's because nature itself doesn't commit to those values until we check. Einstein wasn't buying it. To him, that meant quantum mechanics was incomplete, not wrong, but missing something deeper. He believed there must be hidden variables, things we just hadn't discovered yet, that determine a particle's behavior behind the scenes. He once famously said, "I like to think the moon is there even if I am not looking at it." That might sound simple or even sarcastic, but it cuts to the heart of a huge divide in physics. Because for Einstein, the universe wasn't a stage show that only came to life when the spotlight hit it. It was a self-contained, objective reality, independent of us. We were just spectators, trying to uncover the script. This put him at odds with many of the founders of quantum theory, like Niels Bohr, who argued that observation is fundamentally tied to physical outcomes. According to Bohr, asking what a particle is doing when you're not measuring it is meaningless. The theory only describes what you can observe. Einstein wasn't satisfied with that. To him, a theory shouldn't just predict what we'll see. It should describe what's actually happening. Not just the surface, but the underlying mechanism. And yeah, in some ways, history favored Bohr and the quantum crowd. Quantum mechanics works. It powers your computer, your smartphone, even the MRI machines in hospitals. It's insanely accurate. But Einstein's question, is this really all there is, still echoes. Modern physics hasn't settled the debate. Some physicists lean into the strange, observer-dependent interpretations of quantum mechanics. Others, like those working on quantum field theory, string theory, or even emergent spacetime, are still chasing Einstein's dream. That reality is deeper, more grounded, and doesn't care whether or not we're watching. There's even a branch of thought that maybe consciousness itself plays a role in shaping outcomes. But Einstein would have bristled at that. For him, the universe wasn't waiting on your attention to decide how to behave. It was real. Always, everywhere. With or without you. And that's what made his views so powerful. Not just scientifically, but philosophically. Einstein didn't just want a theory that gave answers. He wanted a theory that made sense. One that reflected a universe governed by logic, consistency, and truth. Not randomness, not ambiguity, not something that depended on an observer clicking record. Because if reality only pops into existence when someone's watching, then what is it, really? Einstein never let go of the belief that there's something real out there. A universe that doesn't flinch when we turn our heads. A cosmos that's not made of probabilities, but of truths we just haven't uncovered yet. And maybe, in the end, that's what science is all about, trying to peel back the layers of mystery, to reveal a universe that's been there all along, whether we noticed or not. Quantum mechanics must be derived from deeper laws. Let's talk about something Einstein wrestled with until the end of his life. Something he just couldn't accept, no matter how successful the math was or how well the predictions matched the experiments. And that's quantum mechanics. Now don't get this twisted. Einstein didn't deny quantum mechanics worked. He respected it. He helped build it. Remember, it was Einstein's own work on the photoelectric effect. The idea that light comes in discrete packets called photons. That helped launch quantum theory in the first place. But here's the thing. Einstein didn't believe quantum mechanics was the final word on how the universe works. To him, it felt like a puzzle with missing pieces. Accurate. Sure. Complete. No way. He believed quantum mechanics was just a surface-level description, something that worked statistically, on average, but that underneath, there had to be a deeper set of laws, something more fundamental, something that didn't rely on chance or uncertainty, but on logic and causality. Because to Einstein, the universe wasn't built on randomness. It wasn't a cosmic slot machine spitting out probabilities. It was a system, an elegant, ordered system governed by principles that, once understood, could explain everything. So when quantum mechanics said things like, this particle might go here, or it might go there, we won't know until we measure it. Einstein basically said, nope, that's not how nature works. We're just not seeing the whole picture yet. Let's go back to that famous phrase, God doesn't play dice with the universe. He wasn't being religious. He was being philosophical. What he meant was nature doesn't make decisions based on probability. It follows rules, real deterministic rules. We just haven't uncovered them yet. Let's take the concept of wave function collapse, for example. In quantum mechanics, a particle is described by a wave, a set of probabilities. But once you observe it, that wave collapses, and the particle shows up in a specific location. To most physicists at the time, this was just how things worked. The math predicted what you'd observe, and that was good enough. But not to Einstein. He wanted to know what was happening behind the math. What's the mechanism? What's causing that collapse? Is it truly random? Or are there variables we haven't discovered yet that determine how it all plays out? This is where Einstein started to drift away from mainstream physics. He began searching for a deeper theory, something that would contain quantum mechanics as a special case, but also explain the why behind its weirdness. Think of it like this: quantum mechanics is like a weather app that's really good at telling you there's a 70% chance of rain tomorrow. That's useful. You know to take an umbrella. But Einstein wanted the atmospheric science behind it, the full-blown meteorology model that explains why the rain forms in the first place. He believed there had to be hidden variables, unknown factors buried in nature that determined outcomes, even if we couldn't measure them yet. This idea became the foundation of what's called deterministic hidden variable theory. It's a mouthful, but the idea is simple: randomness is just a sign that we're missing information, and Einstein wasn't alone in thinking this way. Other brilliant minds, like David Bohm, later developed pilot wave theory, an interpretation of quantum mechanics that does include hidden variables and does assume an underlying determinism. But here's the kicker: these theories are often just as good as standard quantum mechanics when it comes to making predictions. The math works. The difference is in the philosophy, in what we believe is really going on beneath the surface. Einstein's search for deeper laws wasn't just about fixing quantum mechanics. It was about uniting it with general relativity. Because here's the problem: general relativity is all about smooth curves, continuous space, and cause-effect relationships. It's the majestic theory of gravity that treats the universe like a grand, flowing river. But quantum mechanics, that's a totally different animal. It deals in probabilities, sharp jumps, discrete quanta, and uncertainty. Trying to put the two together is like forcing a round peg into a square hole, and Einstein knew it. He spent the last decades of his life searching for what he called a unified field theory, a deeper framework that would combine gravity and electromagnetism, and eventually quantum theory too, into one seamless picture. He didn't find it, but the search didn't die with him. Today, physicists are still chasing that dream. String theory, loop quantum gravity, quantum field theory, emergent spacetime. They're all part of the quest to find the deeper laws Einstein was convinced had to exist. And here's the thing: even though Einstein was wrong about some aspects of quantum mechanics, his insistence on deeper understanding is still respected. He didn't settle for equations that worked. He wanted to know why they worked. Because he believed the universe wasn't just a black box you poke at to get answers. It was something intelligible, something you could understand at a foundational level. So when we say Einstein believed quantum mechanics must be derived from deeper laws, we're talking about his unshakable faith that randomness is an illusion, that underneath the chaos, there's clarity, that physics shouldn't just describe how things appear. It should reveal what's really going on. And maybe, just maybe, those deeper laws are still waiting for us, quietly humming in the background of the universe, just out of reach for now. There's no universal now. Let's start with a simple question that seems obvious on the surface. What time is it right now? Seems easy, right? You glance at your phone, your clock, your microwave, and boom, it's 3:37 p.m. Done. But here's the twist: what if I told you that, right now, might not even exist the way you think it does? That your now might not be the same as someone else's. Not just because of time zones or clocks running slow, but because time itself isn't the same for everyone, everywhere. That's the mind-bending reality Albert Einstein introduced with his theory of special relativity, and it completely shattered the way we think about time. Here's the deal: in everyday life, We treat time like it's a global clock ticking away in perfect sync for everyone in the universe. Whether you're on a beach in Bali or floating on the International Space Station, we tend to think there's a single, shared moment called now. But according to Einstein, there's no such thing. There is no universal now. Let's unpack that. Imagine you're standing still on Earth, and your friend is zooming past you in a spaceship at close to the speed of light. You both have perfectly synced atomic watches. You wave at each other as the ship blasts by, and both of you hit a stopwatch button at the exact same moment, according to yourselves. But here's where things go strange. Those two events, the wave and the stopwatch press, don't actually happen at the same time for both of you. In your frame of reference, you hit the button at the same moment your friend passes by. But from their perspective, you hit the button either earlier or later than they did, depending on their direction and speed. This is called the relativity of simultaneity, and it's one of the most unintuitive, but experimentally confirmed, parts of Einstein's theory. It means that simultaneous events for one observer can happen at different times for another. And once you accept that, you realize something even deeper, that your definition of now, your present moment, isn't absolute. It's relative. It depends on how fast you're moving and where you are in spacetime. This completely destroys the idea of a single, shared present moment stretching across the entire universe. Let's go cosmic for a second. Say you're sitting on your couch watching TV, and somewhere light years away, on a planet orbiting another star, there's an alien brushing their teeth. You might wonder, what is that alien doing right now? But according to relativity, that question doesn't actually make sense. Because right now is different depending on who's asking and how fast they're moving. From your perspective, the alien might be brushing their teeth, but from another observer's perspective, say, someone moving rapidly through space, that alien might have brushed their teeth yesterday, or won't brush them until tomorrow. There is no one definitive answer, so the idea of a single now that applies across the entire universe, that's just not how time works. And it's not just theory. This has real implications. When we use GPS satellites, for example, engineers have to account for the fact that time flows differently for the satellites than it does for people on Earth. The satellites are moving fast, and they're in a weaker gravitational field, so their clocks tick slightly faster than ours. Without correcting for that, GPS wouldn't be accurate. And while that's a practical application, the philosophical impact is even bigger. Because when Einstein showed that time is not absolute, he also showed that our experience of past, present, and future is deeply personal, tied to where we are and how fast we're moving. It's not a fixed backdrop to the universe. It's flexible, it's relative. This idea shook the very foundation of how people thought about time. Before Einstein, time was like a universal metronome, ticking away, same for everyone. Newton believed in absolute time, a constant flow that existed independently of observers. Einstein destroyed that notion. He showed that space and time are intertwined, part of the same four-dimensional fabric we now call spacetime. And once space and time are fused together, you can't treat time like some global stopwatch. It bends, it stretches, and it disagrees from one observer to another. So, the next time you check the clock, pause for a second. What feels like now to you isn't necessarily now to someone else. And if you're ever moving fast enough, like close to the speed of light, that difference becomes undeniable. It's not that time is broken, it's that we misunderstood what it even is. Now, isn't a moment frozen across the universe? It's just a slice of reality from your perspective, and everyone, every spaceship, every star, every observer, has their own, which means, in a weird and wonderful way, We're all living in slightly different universes, not separated by space, but by time itself. And Einstein, he saw this not as a flaw, but as a beautiful truth, a reminder that reality isn't rigid, it flows, it warps. And maybe, just maybe, that makes it all the more mysterious and all the more real. Atomic energy could power the world and destroy it. Let's talk about one of the most powerful and terrifying consequences of Einstein's ideas. Something that changed human history forever, and something he both enabled and feared. It all comes down to a single, deceptively simple equation: energy equals mass multiplied by the speed of light squared. This is Einstein's most famous insight, probably the most famous equation in all of physics. And it unlocked a truth no one had truly understood before, that matter and energy are not separate things. They're interchangeable. They're just two forms of the same essence. This means that even a tiny amount of mass holds an enormous amount of energy, because the speed of light squared is a huge number. You take a grain of sand, almost weightless, and it still contains enough energy to power a small town, if you could unlock it all. That's not an exaggeration. That's physics. Now, at first, this was just a wild theoretical idea. Einstein published it in 1905 as part of his work on special relativity. He wasn't trying to build weapons or reactors. He was exploring the fundamental nature of the universe. But ideas have power, especially ideas about power itself. As scientists began to understand the structure of the atom in the decades that followed, they realized something stunning in certain types of atoms. You could split the nucleus. And when you did, a small amount of the mass disappeared and reappeared as pure energy. That's nuclear fission, and it's the direct application of Einstein's equation. You take heavy atoms like uranium or plutonium, and when you split them, you lose a little mass. That mass doesn't vanish. It transforms into heat, light, and radiation. And because of the speed of light squared, the energy released is enormous compared to the amount of matter involved. This is the principle behind nuclear power, and also nuclear bombs. Here's the twist: Einstein didn't invent the bomb. He wasn't part of the Manhattan Project, and he never worked directly on nuclear weapons, but his equation, and the science that followed from it, made them possible. And when World War II erupted, Einstein realized that this wasn't just a theory anymore. It was becoming real. In 1939, two Hungarian physicists, Leo Szilard and Eugene Wigner, came to Einstein with urgent news: Nazi Germany might be trying to build an atomic bomb. They needed someone with authority to sound the alarm, and that someone was Einstein. He wrote a letter to President Franklin D. Roosevelt, a now famous document that warned of the potential for a bomb of a new type with unprecedented destructive power. That letter helped launch the U.S. nuclear program, the Manhattan Project, which ultimately led to the bombings of Hiroshima and Nagasaki in 1945. Einstein was devastated. Though he understood the necessity of stopping Hitler, he would later say that signing that letter was the greatest regret of his life. He was a pacifist at heart, someone who believed science should serve humanity, not destroy it. And here's the deeper layer of irony: Einstein's equation doesn't care what you use it for. It simply describes a truth of nature. Whether you harness that energy for a city's electric grid or for the core of a weapon, that's a human decision. Einstein once said, "The release of atomic power has changed everything except our way of thinking." And that's the dilemma we still live with today. Because atomic energy can power the world, nuclear plants produce massive amounts of electricity without greenhouse gases. A single pellet of uranium can release as much energy as a ton of coal. And with modern reactor designs, the risk of accidents is lower than ever. But atomic energy also carries enormous responsibility. We've seen the consequences when it goes wrong. In Chernobyl and Fukushima, and in the specter of weapons stockpiled across the globe. So we're left with a paradox, one that began with Einstein's insight. We now hold the power of the stars in our hands, and the question is, what do we do with it? Do we build a future of clean, abundant energy, or do we repeat the past, using knowledge to divide, to dominate, to destroy? Einstein knew the dangers of knowledge without wisdom. That's why, after the war, he became a vocal advocate for nuclear disarmament and global cooperation. He joined forces with philosophers and scientists to promote peace. He wasn't trying to undo his work. He was trying to guide its future. Because that little equation, energy equals mass multiplied by the speed of light squared, isn't just a line in a textbook. It's a reminder of the stakes. It shows us that even the smallest things can have unimaginable consequences, that inside every atom there's a potential for progress or for peril, and it puts the responsibility back where it belongs, not in the laws of physics, but in the hands of people. In the end, Einstein gave us the key. What we choose to unlock with it, that's still up to us. Science and philosophy must coexist. You might know Einstein as the guy behind energy equals mass multiplied by the speed of light squared, the bending of spacetime, and all the wild mind-bending physics we've been talking about. But what most people don't realize is, Einstein wasn't just a scientist. He was also a philosopher, and he didn't see science and philosophy as two separate worlds. In fact, he believed they had to work together, one without the other. That's how we lose our way. Let's break it down. Science is about observation, experimentation, and discovering how the universe behaves. It's data, formulas, test tubes, telescopes, all the stuff you picture in a lab. Philosophy, on the other hand, is about asking the deeper questions. Why does the universe exist at all? What does it mean for something to be real? Is there a purpose? Now, in modern times, especially in some corners of science, there's this tendency to brush off philosophy. Like, if it can't be tested, it doesn't matter. But Einstein didn't buy into that mindset. Not even close. In fact, he once said, "Science without philosophy is blind. Philosophy without science is empty." And that's such a powerful way to put it. See, science tells us how things work, but philosophy helps us reflect on what those discoveries mean, where they fit into the bigger picture, and how we should use them. Without philosophy, we risk becoming technicians, brilliant at building things, but blind to why we're building them or what they're for. Einstein's theories, like relativity and mass energy equivalence, didn't just emerge from experiments. They came from thought experiments. He imagined chasing beams of light. He pictured elevators floating in space. He questioned the very nature of time, space, and reality, all deeply philosophical ideas. In fact, long before he had the math to back anything up, he had questions, big ones. And that's where the spark always starts. One of the reasons Einstein's ideas stood out is because he was never satisfied with just crunching numbers. He was trying to understand the essence of things. What is time really? What is motion? What is gravity beyond just a force? And that mindset didn't just make his science better. It made it revolutionary. He often read and quoted philosophers like Immanuel Kant, David Hume, and Baruch Spinoza. In fact, Spinoza's writings on the interconnectedness of nature and the rational structure of reality had a profound impact on Einstein's worldview. He once said he believed in Spinoza's God, not a personal deity, but a deep reverence for the harmony and logic woven into the universe. So when people tried to divide science and philosophy, treating one as practical and the other as abstract, Einstein saw that as a dangerous split. He knew that when science is disconnected from philosophical thinking, it can become cold and mechanical. We might know how to split the atom, but not how to use that knowledge wisely. This was one of his deepest concerns in the aftermath of World War II. He had witnessed firsthand how scientific advancements could be weaponized, and he believed that without philosophical grounding, without ethics, reflection, and big picture thinking, science could spiral into something destructive. It's not just about knowing more, it's about understanding what knowledge is for. Even today, this idea rings louder than ever. With artificial intelligence, genetic engineering, quantum computing, we're unlocking tools that have incredible power. But the question still stands: to what end? That's not a purely scientific question, that's a philosophical one. And Einstein would argue that if we want to use science in a way that uplifts humanity, instead of endangering it, we must bring philosophy back into the conversation, because philosophy helps us ask better questions, and better questions lead to better science. Einstein didn't just build theories, he wrestled with their meaning. He cared deeply about peace, freedom, and the future of humanity. He saw science not as a cold discipline, but as something deeply human. He once wrote, "The most beautiful experience we can have is the mysterious. It is the fundamental emotion that stands at the cradle of true art and true science." And in that kind of wonder, that sense of awe, it doesn't come from equations alone. It comes from asking, what does it all mean? That's where philosophy steps in. So maybe the real takeaway here is this: science and philosophy aren't rivals. They're dance partners. One builds the ladder to the stars. The other asks if we should climb it. And in a world racing forward faster than ever, Einstein's message feels more urgent by the day. Knowledge without wisdom isn't enough. We need both. Because that's how we stay curious. That's how we stay human. Matter and geometry are interconnected. Here's a thought that sounds almost poetic, but it's actually straight from the most precise physics. We've got matter and geometry are not separate. They are woven together. Now, what does that even mean? Well, for most of history, people thought of space as just empty, a blank stage where stuff happens. You've got matter, like planets, stars, people, coffee mugs. And then you've got space, the vast nothingness they float around in. But Einstein flipped that idea on its head. In his theory of general relativity, he showed that space is not nothing. In fact, it's something. It has structure, it can bend, it can ripple, and most importantly, it can interact with matter. And vice versa. The geometry of space and time is shaped by the matter and energy inside it. And that geometry, in turn, tells that matter how to move. Let's take a real-world example. Imagine the sun sitting in space. According to Newton, its gravity pulls on the Earth, keeping it in orbit, kind of like an invisible tether. But Einstein saw it differently. In his view, the sun doesn't pull on Earth at all. Instead, the sun warps the geometry of space around it. The Earth is simply following the straightest possible path through that curved geometry, kind of like a marble rolling around a stretched-out rubber sheet. It's not force, it's shape. Now take that a step further. If you remove the sun, space would go back to being flat in that region. But as long as matter exists, stars, galaxies, black holes, space is never perfectly flat. It's always being distorted just a little. Even the chair you're sitting on is warping spacetime, though by an absurdly tiny amount. So when we say matter and geometry are interconnected, what we're saying is they define each other. One can't exist meaningfully without the other. Matter gives space its curves. Space tells matter where to go. It's like a cosmic feedback loop. This is exactly what's captured in Einstein's field equations of general relativity. The geometry on one side of the equation equals the energy and momentum of matter on the other. It's literally encoded in math, but the meaning is deeply profound. It means space isn't passive, it's dynamic. It responds to what's in it. And matter isn't just along for the ride. It actively shapes the universe. This idea becomes especially dramatic when you look at something like a black hole. You take a massive star, compress it into an ultra-small point, and suddenly, space around it is so warped that not even light can escape. It's the ultimate example of matter sculpting geometry to an extreme degree. But here's where things get even weirder and more beautiful. In modern physics, especially in the search for quantum gravity or a theory of everything, some researchers are even starting to ask whether geometry itself might be emergent, not fundamental. In other words, maybe spacetime comes from something deeper. Maybe it's built out of information, or quantum entanglement, or some network of more basic bits. But if that's true, then matter and geometry aren't just interconnected. They might be two faces of the same underlying reality. Think about that for a second. The atoms in your body and the space between stars could be made of the same fabric, just shaped differently. Einstein probably wouldn't have been surprised. He always had a gut feeling that the laws of nature were unified and elegant, that the divide between things and space was artificial. To him, the universe was like a great work of art, connected, harmonious, subtle. He once wrote, "Our separation of each other and of time and space is an optical delusion of our consciousness." In other words, we perceive matter and space as distinct, but maybe that's just a trick of perspective. At the deepest level, they are expressions of the same reality. So what does this all mean? It means when you move, when you sit, when you simply exist, you're not floating in an empty void. You are part of a living, responsive, physical fabric. The mass in your body curves the space around you, and that space responds in kind. It also means the universe isn't just filled with objects. It's shaped by relationships. Matter doesn't just sit in space. It shapes it. And space doesn't just allow matter to exist, it guides it. That's the genius of Einstein's vision. He didn't just give us a new way to calculate orbits. He gave us a new way to understand the very structure of reality. The cosmos isn't made of separate pieces, scattered in a vacuum. It's a dance of matter and geometry, a seamless flow, one affecting the other endlessly. And we're part of that equation. The universe had no beginning or end else initially. One of the wildest things about Einstein, despite being the guy whose equations ultimately led to the idea of the Big Bang, he originally didn't believe the universe had a beginning or an end. Seriously. When Einstein first developed his theory of general relativity in 1915, something strange happened. His equations didn't describe a still, unchanging universe. They predicted something dynamic, a universe that was either expanding or contracting. But Einstein, like pretty much everyone else at the time, thought that couldn't be right. The general belief back then was that the universe was static, eternal and unchanging, with no starting point and no destination. And Einstein, he wanted his equations to match that vision. So what did he do? He added a term to his own equations, a sort of mathematical fix. It was called the cosmological constant. This little adjustment added a repulsive force to balance gravity, holding the universe in place like a cosmic scaffolding. Basically, he tweaked the math to make the universe stand still. Why? Because the idea that the universe had a beginning, that it might be expanding, or that it once came from a single point, just didn't sit well with him at the time. It sounded too philosophical, too religious even. So instead, he built a version of the cosmos that had no beginning and no end. A universe that just was, always had been, always would be. But here's the twist. His own math didn't want to stay still. Just a few years later, in the 1920s, a Belgian physicist and priest named Georges Lemaître looked at Einstein's equations without that cosmological fix, and what he found was astonishing. The math suggested that the universe was actually expanding. Then in 1929, Edwin Hubble made a discovery that changed everything. Distant galaxies were moving away from us. Not just some of them, all of them. The farther away a galaxy is, the faster it's receding. And suddenly, the evidence was overwhelming. The universe wasn't static. It was growing, stretching, evolving over time, which meant, if you ran the clock backward, it must have had a beginning. Einstein had no choice but to accept it. He reportedly called his edition of the Cosmological Constant, the thing he used to force a static universe, his greatest blunder. But here's the interesting part. Even though he let go of the idea of a timeless universe, that vision still tells us a lot about how Einstein thought. He wasn't trying to deny evidence. He just believed the universe should be simple, balanced, and eternal, not because of dogma, but because he trusted in harmony, in timeless laws, in a cosmos that didn't need a dramatic origin story to make sense. And maybe he wasn't entirely wrong, because, plot twist, the cosmological constant is back. In the late 1990s, astronomers found that the universe isn't just expanding, it's expanding faster and faster. Something is pushing space apart, a mysterious energy we now call dark energy. And how do we model it? Using Einstein's old cosmological constant. So is called blunder. It might have been one of his greatest predictions. But let's come back to the original idea of the universe, with no beginning or end. While modern cosmology supports a Big Bang, a moment when space and time began, the conversation isn't over. Some physicists are exploring models where the Big Bang wasn't truly the beginning. That maybe our universe is part of a larger multiverse, or emerged from a bounce from a previous collapsing universe. In those models, there may be no absolute start, no true end, just an eternal ebb and flow, and that's kind of poetic, because it means Einstein's instinct that maybe the universe is eternal, in some form, might still be lingering in the deepest layers of modern cosmology. What we now know is that the universe is about 13.8 billion years old. It had a beginning, at least as far as we can currently see. But the question of what came before, or whether time even existed before, is still up for debate. Maybe it's turtles all the way down. Maybe it loops. Maybe time itself is an illusion and there was never a before to begin with. Einstein didn't have all the answers, but his willingness to shape and reshape his views in light of new evidence. That's what made him a scientific legend. He once said, "The important thing is not to stop questioning." And that's exactly what this idea teaches us. The universe might have had a beginning, or it might stretch back into eternity. Either way, the deeper we look, the more we realize this place is far stranger and more beautiful than we ever imagined. Reality might be a product of deeper, hidden variables. Let's talk about one of Einstein's biggest disagreements with the way modern physics turned out, and one of the deepest philosophical questions in all of science. Is reality really random? Or are we just missing something? When quantum mechanics started rising in the early 20th century, it flipped everything on its head. Particles weren't just little marbles following predictable paths anymore. Instead, they became probabilities. They could exist in multiple places at once. Their properties weren't set until they were measured. It was strange. It was brilliant. And it worked. But Einstein, he wasn't buying it. At least, not all of it. He didn't deny that quantum mechanics was useful. In fact, he helped launch it with his work on the photoelectric effect, where he showed that light comes in packets, or quanta. But as quantum theory evolved, especially with the rise of the Copenhagen interpretation, which said particles don't have definite properties until they're observed, Einstein started to push back. He wasn't okay with a universe that rolled the dice. That's where his famous line comes in: God does not play dice with the universe. What he meant was this: the randomness we see in quantum mechanics might not be true randomness. It might just mean we don't have the full picture yet. He believed there could be hidden variables, things going on beneath the surface that we don't yet understand. Variables that would bring order to what looks like chaos. A deeper layer of physics, still waiting to be uncovered. Think of it this way: imagine you walk into a casino and you see a roulette wheel spin and land on red. Then it spins again, red, again red, over and over. If you only saw the results, it might seem completely random. But if you had access to the mechanics, the exact speed, friction, angle, everything behind the scenes, you could, in theory, predict where it'll land. That's how Einstein thought about quantum particles. Sure, they looked unpredictable, but maybe that's because we didn't yet have the tools or knowledge to peek behind the curtain. In his view, reality was still real. It existed whether or not we observed it, and particles had definite positions, velocities, and properties. We just couldn't see them clearly. But most quantum physicists at the time, and even now, disagreed. They said randomness wasn't a sign of ignorance. It was fundamental. That's just how the universe works at the smallest scales. So who was right? Well, it gets even messier. In 1964, physicist John Bell came along with something called Bell's theorem, and what it showed was revolutionary. Bell proved that if hidden variables do exist, they can't behave in a way that respects both locality, the idea that objects can't instantly affect one another across space, and realism, the idea that physical properties exist independently of observation. In other words, if quantum mechanics is correct, and all the experiments so far say it is, then Einstein's vision of local realism can't be fully right. It was a huge blow to the hidden variables idea, or at least to local hidden variables. Some physicists still try to develop non-local hidden variable theories, like Bohmian mechanics, which offers a deterministic version of quantum mechanics but allows for spooky connections. So while Einstein's dream of a tidy, deterministic universe hasn't totally vanished, it's taken some serious hits. Still, the idea of deeper laws beneath quantum mechanics hasn't gone away. Many physicists are still unsatisfied with the randomness baked into standard quantum theory. They think, just like Einstein did, that we might be missing a bigger picture. Maybe quantum mechanics is like Newton's laws, useful and brilliant, but ultimately just a stepping stone to something deeper. There are even modern theories exploring this idea. Approaches like superdeterminism, pilot wave theory, and quantum gravity frameworks suggest that quantum weirdness could emerge from more fundamental structures. We don't know yet, but the question is still alive and very much open, because at the heart of it all is a huge, beautiful mystery. Is the universe truly random, or is what we call randomness just a shadow of something deeper, something we haven't discovered yet? Einstein leaned hard into that second possibility. He believed reality was objective, that it existed independently of what we think or measure. And more than that, he believed the universe was ultimately intelligible, that it made sense. So even as he got older and the rest of physics started embracing uncertainty and probabilities, Einstein kept searching. He never gave up on the idea that beneath all the noise there was signal, that beneath the quantum fog there were rules, and that someday, somehow, we'd find them. Whether he was right or not, that mindset, the refusal to settle for surface-level chaos, is part of what made Einstein so powerful. He believed in a deeper reality, and who knows, maybe one day we'll uncover it and realize that what we thought was random was just waiting to be understood.